हो हो हो. झालं चालेल. दोडमणीला पोहोचतो. दोडमणी Good morning, all. Am I audible? डॉक्टर गोकावी सर, हेड डिपार्टमेंट ऑफ केमिस्ट्री 5 मिनिटात जॉईंट होत आहेत आपल्याला, आणि ते आलेत की आपण लगेच सुरू करूया. 5 मिनिटं फक्त लागतील त्यांना यायला.
नाही ते मी ते व्हिडिओ लेक्चर आहे ते बघायचं होतं ते समजणं झाले कसं.
Hello. Good morning to all of you. Namaste. Namaste.
सुरू करा.
Good morning all. Myself Good morning all. Myself, Dr. Kishore Vinayak Gaikwad, the coordinator of today's workshop. I welcome all of you to the workshop organized by Rayat Shikshan Sanstha's Rajarshi Chhatrapati Shahu College, Kolhapur, in collaboration with Shivaji University, Kolhapur, on the topic entitled Change in Syllabus of M.Sc II Semester 3 Physical Chemistry course. The main intention behind organizing this workshop was to enlighten chemistry teachers fraternity regarding the new changes introduced by the university with the revised syllabus. I thank the university authorities for giving us an opportunity to organize this important activity in our college. In today's workshop, the keynote address will be given by Professor Dr. G.S. Gokavi sir, the head Department of Chemistry, Shivaji University, Kolhapur. Then today's presidential speech will be given by an honorable principal of our college, Principal Dr. S.T. Saunke sir. Then the invited talk will be arranged on changed syllabus by the BOS member, Honorable Professor Dr. D.H. Dagde sir, Professor Dr. G.B. Koyekar sir, Professor Dr. G.S. Gokavi sir, Professor Dr. K.M. Garadkar sir, and my friend Dr. S.N. Taide sir. With this introduction, I request Honorable Professor Dr. G.S. Gokavi sir to give the keynote address. Over to you, Gokavi sir.
Okay, thank you. Thank you and good morning to all of you. Today, as Professor Gaikwad mentioned, I think we have assembled here through online by Zoom meeting to discuss the new changes in the syllabus of MSc Part 1, MSc Part 2. So as far as MSc Part 2 physical chemistry is concerned, I think the resource persons and as well as the participants in this particular session or in this particular workshop, they should give more highlights on how the students can be attracted towards our physical chemistry. Because most of the time, as since myself and Professor Dagade has just now completed the admission process, during that we have experienced that almost the last chance would be given to the physical chemistry. But whereas the applications of physical chemistry are much more than other branches of this one. You cannot consider this as an inferior course. Because as our experience is concerned, I think day before yesterday or in the last week, I think you might have read an article in Sakar regarding Balchandra Kakade. I think Balchandra Kakade is a physical chemistry student from our university. Most of the people doesn't know that. And Balchandra Kakade has worked in fuel cells as well as in water splitting reactions. Now he is having a very good projects and he has very good patents to his credit. And he belongs to our own physical chemistry student. Another aspect I want to mention it, that along with Professor Dagade is there, we have two other students who are doing very good in physical chemistry. One is Anant Kulkarni, who is almost editor of most of the journals of physical chemistry, including American Chemical Society, Royal Chemical Society. So he is also one of our alumni. Alumni in the sense physical chemistry alumni. So, and he is in the business of software. He can write softwares. These people are doing very good at the physical chemistry level. You want to name some of them? I think some of our students are also having projects in their hand as far as organic chemistry is concerned. Even some of them are also doing very good in inorganic chemistry in Korea. I think few alumni of our department are working as professors in this one, and they are working in material science. And material science, basically, the material itself is an inorganic of nature. So therefore, they are also doing the very good work in inorganic chemistry, even though their basic training or their basic degree is physical chemistry. So having physical chemistry may not be a hurdle for your career development, but it will help you to build up a career in any branches of the chemistry. So that aspect has to be brought to the students, especially in case of BSc students, so that they should not get any regrets after getting an admission into MSc Physical Chemistry. So that should be your motto. In that respect, we have changed a little bit our MSc Part 2 syllabus along with my colleagues in the department, that wherever necessary, we have combined, for example, electrical and magnetic properties have been combined in molecular structure 2. And then we have introduced a new chapter, which is of current importance, that is the fluorescence spectroscopy, which I think most of the research is going on. As far as now we are getting the output of that one, that is LEDs and other aspects, because it has been started with only the liquid crystals as far as display is concerned. Now it has come up to LED, and LED, LCD, all these things have been the developments done in case of fluorescence spectroscopy or the materials having fluorescence characteristics. So therefore that has been introduced into the syllabus, and just to include that one, we have just combined two of our important this one, that is electrical and magnetic properties together. Then other aspects, I think in case of quantum chemistry also, it has been new topics have been introduced, and in kinetics also new topics have been introduced. Electrochemistry, I think it has been changed. We have reverted back into the original this one. So all these changes have been made, but the main focus as far as physical chemistry teachers are concerned should be to motivate the students to learn physical chemistry. And if you prepare them well as a postgraduate students or postgraduates in physical chemistry, they can further go in at the college level, and then they will also motivate the students of uh, degree students. So I think that would be the motto for present day workshop. And rather than, I think you can get more material even through online also regarding your teaching is concerned, but more should be, as I feel, that more should be discussed on the scope of the subject, significance of the subject, and the motivation of the students towards the physical chemistry. Yes. So that is what I feel is important as far as this workshop is concerned. I thank the authorities of Shivaji University for granting you the workshop, this one. And I also thank the college principal, Dr. S.T. Salunke, and Dr. Gayakwad, Dr. Pawar, and Dr. Dodmani for inviting me and participating in this workshop. Thank you, one and all.
एक minute. Now I request our honorable principal sir to preside over the workshop.
Good morning, all of you. I welcome on the behalf of Rajashri Shahu Chakrabarti College, Dr. G.S. Gokavi sir, Head of the Chemistry Department, Shivaji University, Kolhapur, and all colleagues from University Department. Also, I welcome all staff members on the behalf of for this one-day workshop on changing syllabus for M.Sc. Part 2. As far as concerned strength of the students for M.Sc. Part 2 Physical Chemistry, out of 20 colleges, only 2 colleges are running this course, particularly Islampur and our Shahu College. And in addition to this, we have strong University Chemistry Department, Physical Chemistry. Being a student of Physical Chemistry, I am happy to organize this workshop. As far as concerned syllabus of the M.Sc. Part 2, nowadays there is very attractive knowledge in artificial intelligence, machine learning, operation research. We have studied statistical thermodynamics, quantum mechanics, and electrochemistry. Post to this syllabus, now we have to go to these new subjects. Just I have mentioned here, artificial intelligence and data science. So physical chemistry can play much bigger part in this modern technology era, and we can get more employability for students passing or completing their research in physical chemistry or doing their postgraduate in our branch. So I request all of you to modernize this syllabus, software oriented and correlated to these subjects as far as data science is concerned. So data is a big thing in coming years. So now there is less interest of students to take admission for M.Sc. Physical Chemistry. So increase interest of student and employability, we have to join, or we have to take linkage between industry and academics. And that way, on that line, we are going to organize foundry course also to technology with collaborating with industry. The demand of industry and supply from academics is important factor regarding syllabus modification. So I request all of you to do needful regarding strengthening your syllabus. Best luck for this syllabus. Thank you. Syllabus. Thank you.
Thank you, sir. Thank you very much. Now I am here to introduce our today's first resource person, Professor Dilip H. Dagde sir. Sir is presently working as a professor in physical chemistry at Department of Chemistry, Shivaji University, Kolhapur. Sir has completed his B.Sc., M.Sc. and PhD from Shivaji University, Kolhapur. Sir is having a basic research interest in thermodynamics, molecular simulation, NIR spectroscopy, hydrogen bonding, and ionic hydration. Sir is having 21 years of rich teaching experience for PG, and sir is also working as a research guide for MPhil and PhD students. So far, 6 students completed their PhD work under the guidance of him. Sir is also completed 3 major research projects and from different funding agencies like ACRB, UGC, and Shivaji University, Kolhapur. Total 55 international publications on his credit. He also having a membership of prestigious committees, also received awards as Professor Shanti R. Palit Young Scientist Award, reviewer for many international journals, Best Research Paper Presentation Prize, and Best Research Paper Presentation Award. With this brief introduction, I request Honorable Professor Dilip Dagde sir to guide all us. Thank you, sir. Over to you, sir.
थँक यू व्हेरी मच किशोर. सो आवाज येतोय सर्वांना?
Yes, sir. Yes.
Yes, okay. So thank you for a kind introduction. Honorable Professor Gokavi sir, Principal of the college, Salunke sir, Coordinator Gaikwad sir, and other participants of this workshop. First of all, I am thankful to the organizing committee as well as principal of the college for inviting me to act as a resource person for advanced quantum chemistry course. So in this course, we will see what topics are there and what is the purpose behind introduction of this course at MSc level and advancement of the syllabus or upgradation of the syllabus. Most importantly, as mentioned by Professor Gokavi sir as well as Salunke sir, our education must integrate social relevance as well as national growth, and keeping in mind the today's power and utility of computational chemistry in understanding the science at molecular level, its applications in pharma sectors, its applications in protein chemistry, as well as electronic structure calculations, and understanding the experimental findings or interpretation of the experimental findings. You need the molecular level information for scientific processes. So keeping in mind all these things, we have designed a course named as Advanced Quantum Chemistry. So once this course is being taught to the students will be able to understand the concepts of atomic orbitals, their shapes, how to find out the selection rules for the spectral transitions, ionization potentials, etc. If they learn advanced quantum methods such as HF-SCF theory as well as post-HF methods that is required for the doing electronic correlation energy estimation, that is the correction to the HF energy. So using these, student can be able to do the electronic structure calculations and accurate energy as well as molecular structure optimization can be performed for any molecules. Then knowledge of this course will lead to do a computer simulation to calculate molecular properties, NMR shift, IR, Raman spectra, UV visible spectra, or any molecular property that you can name. All these properties you can evaluate once you are able to do a computer simulation using these advanced ab initio methods. Then also, if we want to find out the appropriate method for doing the electronic structure calculations, for understand or for calculating the molecular properties, you must know what type of the basis sets and basis functions one has to choose. For that purpose, we must learn the basis sets. So all these things are there behind introducing this advanced quantum chemistry at the master level. And I am happy to inform all of you that this is the one of the best course in the country and even also in the world class. If you look towards the syllabi at international universities, even top 50 universities, then also you will find that our course is equivalently better or even better than their courses if we look towards the syllabus. Only thing is that we have to inform our students about the importance of this course, and we have to teach this course by heart, as well as student has to take it seriously, and we have to introduce the techniques, tools with the help of which student will be able to understand this in a better way. And for that, we have to also give student the computational resources and demonstrate how the calculations can be performed with the help of these new concepts and how they can be extended for the real chemistry or real time applications. So with this brief introduction, let us turn towards the actual syllabi of this course. Okay. So this course is at M.Sc. Part 2 Physical Chemistry. Paper number is 9, semester 3. Name of the course is Advanced Quantum Chemistry. So the first unit, 1 minute. First unit is the basic quantum chemistry. Whatever the syllabus that is being introduced at the M.Sc. Part 1 level, that is quantum chemistry, and that is being extended to have more information, that is how to solve the Schrodinger wave equation from simple systems to little bit complicated systems, and find out the exact solution for the Schrodinger wave equation for rigid rotator. If we solve this Schrodinger wave equation for rigid rotator, then student will be able to understand the microwave spectroscopy, that is rotational spectroscopy, how the selection rule can be evaluated, and how the electronic transitions can occur. So all these informations student can learn from this rigid rotator. Then linear harmonic oscillator, that is the basis of vibrational spectroscopy. Then hydrogen atom and hydrogen like atoms, that is the real chemical systems. That is the simplest chemical system is the hydrogen atom, which contains 1 electron and 1 nucleus. And how the this system one can solve by means of Schrodinger wave equation, obtain the solution as the final wave function. And once you get the wave function, with the help of that wave function, you can calculate what is the probable distance of electron from the center of the nucleus. That is by means of using your expectation value theorem, average distance of the electron you can obtain, and one can compare this with Bohr atomic radius, and you will find that both values comes out to be same. So then also one can find out probability of existence of electron at a given instant of time in a given volume element, that one can evaluate. Also one can find the energy ionization potential for the hydrogen atom or any other atoms containing 1 electron, that is hydrogen molecule ion, helium plus ion, lithium 2 plus ion, beryllium 3 plus ions, and so on. These are called as hydrogen like systems. And how the increase in Z, that is the atomic number increases, then or mass of the atom increases, how the radial distance gets affected. That is the probability of finding the electron get changed as a function of Z. One can find out. Then ionization potential, similarly one can find out and compare the different ionization potential and what is the charge effect. That is Z square. Charge effect on the ionization potential for these hydrogen-like systems. And this is the basic requirement for the understanding of the chemical science. Also, most important thing one can learn is the shapes of the atomic orbitals. What are the shapes of s orbitals, p orbitals, d orbitals, f orbitals, and so on. Those shapes one can calculate with the help of wave functions and explain why p orbitals are dumbbell shaped, s orbitals are spherical, and so on. So these basic information one can find out, and later on we will see the similar information or whatever the information we have learned after solving the exact Schrodinger wave equation for hydrogen or hydrogen-like systems. That wave functions are very, very important for multi-electron systems, even though we are unable to till today solve the Schrodinger wave equation for the multi-electron systems. But whatever the informations we get or what we learn after solving this Schrodinger wave equation for one electron system, just like hydrogen or hydrogen-like atoms, those informations are very crucial and they are basis for the development of advanced quantum mechanics, that is ab initio methods or other higher order methods. Then atomic orbitals, radial and angular shapes of the atomic orbitals, these you can find out. Then also ground and excited state energies one can calculate. Then ionization potential for hydrogen-like systems one can find out. Then transition dipole moment integral, that is the selection rule. One can obtain whether the given transitions are quantum mechanically allowed or whether they are quantum mechanically forbidden. Not only for electronic transitions but also for rotational and vibrational transitions one can find out. And all these are the basis for any molecular spectroscopy, atomic spectroscopy, as well as it is a basis for the advanced quantum mechanics, that is ab initio methods, semi-empirical methods, density functional theory, and post-HF methods. So this unit is very, very fundamental and very, very important, without which no one will be able to understand ab initio methods or other higher order quantum mechanical methods. And today's research is entirely based on that is high standard research is entirely based on doing the DFT calculations, ab initio method calculations, and interpreting whatever the spectral results you get which are difficult to be interpreted. All these can be interpreted with the help of quantum mechanical calculations once you are able to do those calculations, and it is only possible after learning the this course, advanced quantum chemistry. Actually its name should be computational chemistry, but it is difficult to synchronize this with the concepts of the syllabus. That's why it is being kept as advanced quantum mechanics. Then the second unit, whose fundamentals are there in the first unit, is the ab initio methods. Its name itself indicates ab initio means based on the first principle calculations, and your first principle is the Schrodinger wave equation. So methods based on Schrodinger wave equation are called as ab initio methods, and these ab initio methods will student will learn from this unit. Okay, so it starts with self-consistent field theory. Later on we will see why the name for self-consistent field theory is given. So whatever the point I am mentioning here, those points has to be taught to the student, so that student will be able to understand the things completely and will be able to implement those things in an actual computational chemistry calculation, so that they will be able to handle the real life problems as well as current research problems. So the teacher teaching this course must give detailed information to the student so that student will be able to get deeper and deeper information about this course. So self-consistent field theory. So later on we will see why it is being called as self-consistent. So to handle multi-electron systems, for example, I will show you one equation. Suppose you can see this. This is the Schrödinger wave equation for hydrogen atom. So in this equation, you can see that this is the simple Hamiltonian. So this part is the nuclear kinetic energy, right? And this is the nuclear kinetic energy, and this part is the electronic kinetic energy, and this is the potential energy. Now this is being written for the hydrogen electrode. Now if we hydrogen atom, now if we go for the hydrogen molecule ion, another one electron system. So now you can see that this is the kinetic energy of electron 1, that is this is the kinetic energy of nucleus A. This is the kinetic energy of nucleus B. So this term is the electron nucleus interaction energy, that is nucleus A and electron 1. This is the nucleus B and electron 1, and last is the interaction energy, that is nuclear repulsion energy. So this is attraction energy, this is attraction energy, this is a one electron system, so it can be easily solved. Our Schrödinger wave equation can be easily solved. Now if we go for the two electron system, for example helium atom, where is the problem? Now if we look, one can treat this as a one electron system and write Schrödinger wave equation. It will be, this is the kinetic energy of the electron, this is the nuclear kinetic energy, then this is the potential energy for electron nucleus interactions. Now if we take this part, then one electron system will be like this, then this is the nuclear energy and this is the potential energy for this. Now this is a combination of two one electron systems, right? Now but what about this and these two electrons, and their interactions are occurring to one another, and it is being given by this last term, that is E square upon R12. So it is electron repulsion energy, and this electron repulsion energy makes it impossible till today solving the Schrödinger wave equation. That's why only one electron system for which the Schrödinger wave equation one can solve it perfectly, but approximate solution we will get if the system contains more than one electrons. Similarly, you can write an equation for the hydrogen molecule, and which contains two nuclei, two electron. Then you can take the multi-electron atoms or multi-electron molecules, and accordingly you can write an equation for multi-electron systems, and generalized form of that equation is this. So first summation represent the kinetic energy of the electron, second summation represent the kinetic energy of the nuclei, k nuclei, then third term represent the interaction between nuclei and electron, last term represent the interactions between nuclei and nuclei, that is the repulsive interactions, and this term is the complicating term. If this term is absent, then one can easily solve the Schrödinger wave equation for multi-electron systems. However, this term makes it difficult to handle the Schrodinger wave equation or solve the Schrodinger wave equation for multi-electron systems, and this is a electron-electron repulsion term. Then, if this is the case, then how to apply quantum mechanics for the multi-electron systems? And this is the reason why these ab initio methods are there. Okay, so now let us return back to the ab initio methods. So this Hartree-Fock method. This method is developed by Hartree and Fock. These are the names of the scientists for multi-electron systems, and this method is just very similar to whatever the method you have learned, or student can learn in your focal molecular orbital theory. That is the variation principle. Approximate methods, variation principle. Variation principle in which one can assume a trial wave function for a given system and apply the variation theorem, and then minimize the energy, then obtain the coefficient, then back substitute the coefficient into the wave function, then refine the wave function, then again use, and this will be done unless and until your final energy and the energy in the earlier step, this energy doesn't have much difference. So that is called as a self-consistent. So once the self-consistency is achieved, one can call it as a self-consistent field method. So Hartree and Fock developed the self-consistent field method for multi-electron systems, whether they are atoms or the molecules. Only thing is you have to assume a trial wave function, and that trial wave function one can assume in such a way that whatever the wave function you have assumed, that wave function must satisfy the boundary conditions of the system, and that what are the boundary conditions that the student have learned in their M.Sc. Part 1 syllabus. That is, wave function must be finite, continuous, single valued. Their first derivative must be continuous one. So all these information they can use here for selecting the trial wave function. अडचण नाही ना काय?
No sir, no sir.
Okay. Then in this HF method, only thing is that basis sets, basis functions one can use for doing the calculations. These are the well optimized functions that is used in the quantum mechanics, and in Ockel theory you assume a trial wave function, but instead of that trial wave function, these basis functions have been optimized at atomic levels, and they have been used in the molecular level calculations in the Hartree-Fock method. This Hartree-Fock method is an iterative method, and that iterative cycle is given in different books. Those cycles teacher has to explain to the student so that they can understood this in a better way. Then quantum particles, their spins, the spin spatial orbitals are there, and spin included orbitals are also there. So, and while considering the spin wave functions, we have to take into consideration the Pauli's exclusion principle, and also the properties of the Slater determinant we have to take into consideration. That is, interchange of the spin of the electron must change the sign of the wave function. That is, asymmetric nature of the electronic wave function has to be explained to the student. Then we have to formulate the HF equations, what is a Fock operator, then Fock determinants, and so on, and how to solve those Fock equations, Fock determinants, how to calculate the probability, densities, coefficients, electron densities, and so on. That can be learned in the HF theory. and then one can go for the restricted Hartree-Fock theory and unrestricted Hartree-Fock theory. If your valence shell orbitals are contains the paired electrons, then you can use the restricted Hartree-Fock theory. And if unpaired electrons are there, that is each electron being assigned a separate atomic orbital or molecular orbital, then you can use the unrestricted Hartree-Fock models. But unrestricted Hartree-Fock models doesn't obey your eigenvalue, eigen equation for the spin operators. But in case of restricted HF model, whatever the fundamental principles of angular momenta as well as quantum mechanics are there, all these are followed, so that RHF theory is being generally preferred over UHF models. And sometimes UHF models give you the energy, final energy, which is very low than the expected energy calculations. Okay. Then Fock matrix, HF calculations, then Rutherford equations. These Rutherford equations are just like in Huckel theory, whatever the expressions you get finally after solving the secular determinants, similar equations one can get after solving these Fock equations. These are called as Rutherford equations. Then Koopman theorem, that is energy of the outermost shell of the electron is also called as an ionization potential. That is the Koopman theorem, that one can state with the help of those final equations. Then important part of these methods is the basis sets. Slater type orbitals, Gaussian type orbitals. So Slater type orbitals are designed by Slater, and Gaussian type orbitals have been designed by Pople. So Slater type orbitals, those orbitals are similar to that of the atomic orbitals we obtained, that is the wave functions we obtained after solving the Schrodinger wave equation for hydrogen atom. So whatever the functional forms of those hydrogen atoms are there, wave functions of the hydrogen atoms are there, similar functional forms has been taken into consideration for multi-electron systems by Slater. That is angular part is same as it is, and radial part is written in terms of exponential function, exponential raised to minus alpha r, and that alpha exponent is adjusted in such a way that whatever the calculated values, whatever the calculated shape of the atomic orbital in multi-electron system is there, that shape resembles to that of the shape in the hydrogen atom atomic orbital. So unless and until that achievement is there, optimization is being continued, and finally the optimized orbitals can be used further in the molecular structure calculations as well as calculation of electronic properties. Okay. And but what happens due to that e raised to minus alpha r function, exponentially decaying function, this Slater type of the orbitals are very, very difficult to use in the computational chemistry because of the computational time or computational cost, one can say that, required in doing the electronic structure calculations with the help of Slater type orbitals, although they are very accurate one. So since it requires a very large computational energy, that means whatever the calculations you can perform with the help of Gaussian type orbitals, same calculations if you want to perform, then you will require even more than 10 times the time for the calculations. So alternative is the Gaussian type orbitals, and beauty of these Gaussian type orbitals is that if you take one Gaussian function, that is of the form some pre-exponent factor is there, and then exponential raised to minus alpha r square, that square makes it a very faster decaying function as well as doing the calculations very accurately. Faster. The Gaussian type orbitals, those orbitals, its beauty is that if we combine two Gaussians, then resultant function is also a Gaussian. If we combine three Gaussians, then resultant function is also a Gaussian. If we combine hundreds of Gaussians together, then the resultant function is also a Gaussian function. That means only you have to change the alpha exponent, even though you are mixing the large number of Gaussian functions. So calculational method doesn't get changed. That means initially set calculational approach can be extended for hundreds of Gaussian. If you combine together, then that function can also be handled by the simplest form of the algorithms. That's why the calculations are faster one, and Gaussian type orbitals can be used. Then you have to give the information to the student what is the difference between STO, GTO. You can represent it graphically, how the cusp in the STOs is there, that cusp is absent in the GTO. Whatever the shapes that is being observed in the STO, how to reproduce that shape in the GTO. So how these GTOs can be used in the electronic structure calculations. First, for all atoms, STOs is being optimized, and once those STOs is being optimized, then for the same atoms, one can optimize the GTOs. That is, whatever the shape of STO is there, that shape is being produced by means of combining 1 Gaussian, 2 Gaussian, 3 Gaussian, 4 Gaussian, and so on. So linear combination of these Gaussian type functions one can take, so that that linear combination will reproduce the shape of the STOs. And in this way, GTOs are optimized, and once they are optimized, they are fixed one, and their linear combination is being taken to do the electronic structure calculations for the molecular systems or larger systems. So energy calculations using such orbitals for multi-electron systems. Then classification of basis sets. So we have to give the classification of the basis sets. What is meant by a minimal basis set? Then what is GTO type, Popol type of the basis sets? Then what are the representation symbols that is being used in the basis set representation? For example, one can write a 3, 2, 1 G basis set. So what this 3 represent, what this 2 represent, 1 represent, and this G means a Gaussian. 3 means now here is a hyphen sign. So whatever the number before the hyphen sign is there, and whatever the numbers those are after the hyphen sign, they have different meaning. So your any atom, if you take except hydrogen and helium atom, all other atoms contain the core electrons as well as valential electrons. Then these core electrons one can handle by means of this, valential electron one can handle by means of this term. Okay, so like this, that is 3 Gaussians are required to represent a 1 basis functions for each core orbital, and then valence orbital, each valence orbital is being represented by 2 basis functions, one made up of 2 primitives and another made up of only 1 primitives, and this G is for Gaussian. Then if you want to include a what you can say that polarization on the electronic clouds, then you have to include a single star. Single star means addition of D type of the functions to the p orbitals of heavy atoms, and double star, that means polarization on the light atom, that is hydrogen or helium atoms, can be taken into consideration by inclusion of additional virtual p orbitals, 3p orbitals or Gaussians representing the p orbitals can be added. This then diffuse function, that is if you want to handle anions, all these informations one can include in this basis functions or basis sets. So minimal basis sets, then double and triple zeta basis sets, valence split basis set, polarized basis set, etc. can be done. Then truncation and superposition errors, that is infinite number of basis sets are required to achieve the HF limits, but infinite number one cannot use, so finite basis sets has to be used, and that leads to the truncation of the basis sets. And whatever the error in the use of finite basis sets is resulted, that error is called as a truncation error, and that can be optimized by using or minimized by using the optimum basis functions or basis sets. Then superposition error is also there. That means some weakly interacting systems, for example, formation of dimer is there, then you can take the basis functions for the monomers. But for dimer, two molecules are there, double number of basis functions are required, so that mismatch leads to the error called as a superposition error. Then that error can also be minimized, and we have to explain to the students what are the methods to overcome these errors. And then exact energy of the system and HF limit, that difference is called as a correlation energy. Okay, because the reason behind this correlation energy is that HF theory is developed on the assumption that, central assumption is that in multi-electron system, each electron is being considered under the influence of average potential resulted due to the all electrons in the system and nuclei. That average potential is treated as a single nucleus like part, and that electron under consideration is one electron. That is, this is a just one electron like system. Similarly, next time take the next electron, and remaining electron and nuclei as a potential influencing on that particular electron. So in this way, this multi-electron system in the purview of one electron system is handled in the HF theory, and that ignores electron-electron interactions or direct correlations, and that ignorance lead to the error of electron-electron correlation energy. And that electron-electron correlation energy one can account by means of treating the same system using the post-Hartree-Fock methods. There are different methods, configuration interactions, excited state functions. One can find out and develop the equations how to treat these excited state functions: singly excited, doubly excited, triply excited, quadruply excited, and so on. And accordingly, the additional terms will be there. Based upon that, different configuration interaction methods are there. Then many body perturbation theory. You can choose the initial energy calculated using HF theory as a basis for that perturbation theory, and add the perturbed term and find out the perturbation parameter, and then calculate the energy and account the correlation energy. That is called many body perturbation theory. Then molar preset perturbation theory is extension of that. Then coupled cluster theory, in which cluster operator is defined, and with the help of that cluster operator one can also evaluate the correlation energy. And then one can introduce to the students what are the software packages that are used for performing these HF and post-HF calculations, that is ab initio calculations. And there are many open source softwares, just like your GAMES, then other softwares are also there. For example, QChem is there, then NChem is there, then also many open source quantum mechanical software. Quantum Espresso is also there. Many quantum mechanical softwares are there. And for visualizing the results, there are two softwares that are openly available. One is the Avogadro, and one more is the GabEdit. And GabEdit can also be used for generation of input files for those softwares and visualization of the results after doing the calculations. So once these concepts are introduced to the student can independently perform the calculations for some simple system, that is single water molecule, methane molecule, CH2, some anions, some cations, then salt systems, and so on. So and find out the interaction energies, their IR spectra, Raman spectra, then NMR chemical shift, and so on. So whatever the molecular property, that is dipole moment, then heat of formation, thermodynamic properties, and so on. Many things one can evaluate once a student are able to understand this unit. Then next one is the density functional theory. That is electron density. Only difference, main difference between density functional theory and your ab initio methods. These ab initio methods and density functional theory is, instead of using the wave function, what is to be used? This electron density is to be used as a basis or basic variable in the calculations. Okay. Basic variable in the calculations. Then one more thing is common in this case, in this DFT, is whatever the approach that student learn in HF theory, that is how to formulate the HF theory and how to do the iterative type of the calculations in the HF theory. Just I will show you. Just I will show you one more. Okay, now this is the iterative procedure for HF calculations. So initially choose the set of basis functions, then formulate the set of trial coefficient, that is construct the wave functions using these basis functions. Then these are the coefficients. Okay, so these are the coefficients. Then once you find this coefficient, for that formulate the Fock operator, then construct a Fock matrix. Similarly, formulate a overlap integral, then construct a overlap matrix. Then using Fock matrix and overlap matrix, then solve this determinant to calculate the energy coefficient and see whether the convergence is appeared. If no, then repeat the cycle. If yes, then stop the calculations. That is your final energy and final wave functions you will get. And electron density or bond order you can calculate for each pair of atoms with the help of this equation. Once you have this CLU or CMU coefficient you obtained, that is from in this wave function. Okay, so this is a simple optimization cycle in HF SCF calculations. So similar procedure is exactly there in your density functional theory. So in this density functional theory is also the same is there. Only thing is that instead of wave function, you have to use electron density as a basic variable, and then one can use, then you have different theorems, Cohenberg-Cohen theorem, then energy functionals. Functional means what? Instead of function word, it is being used as a functional. Functional means it is a function of a function, and result of which is a pure number. So density functional means it is a function of electron density. Electron density is itself a function of what? A wave function. So density functional means electron density can be treated as a one variable, and which is a function of the wave function. So function of a functional function of a function is nothing but a functional. Okay. So this. So energy functionals are there and other functionals are also there. Minimizing energy orbitals and non-interacting reference systems one can choose. Then Cohen-Sham equations, whatever the Rutherford equations are there, exactly same equations are there. Method is same, only the symbols are different. Instead of wave function, there is electron density. Then computing total energy, then exchange correlation energy functional. This exchange correlation energy functional is slightly different. That is, in case of perturbation theory, the basic known energy is being taken, or ground state energy is being taken as a known system, and additional terms are called as a perturbed terms. In the same way, whatever the multi-electron system is there, if that multi-electron system, if we handle with the help of HF theory, as well as which contains the core electron Hamiltonian, that is 1 electron Hamiltonian, that energy is being calculated, and that energy is being treated as a known energy, and the additional term which is generally represented as Vxc. Vxc. So this term is called as a potential due to exchange and correlation of the electrons, electron-electron exchange and electron-electron correlation. So those two terms, which is a combination of two potentials, that is, one is exchange potential, another one is the correlation potential, right? So total potential is called as a exchange correlation potential, and it is a function of electron density, so it is being labeled as a exchange correlation energy functional. So then solving the Cohen-Sham equations, just like your Fock matrix and Fock determinant, solving Fock matrix and Fock determinant, similar method or exact similar method is used for solving the Cohen-Sham equations. Then basis sets, just like basis set you use in the ab initio methods, similar or same basis sets one can use in this electron density theory or density functional theory. In this DFT, only different is that instead of using wave functions all the times, initially wave functions from the basis sets being calculated, first electron density is calculated, or it is being assumed as a trial electron density, and that is being used in the determinant to obtain the final electron density, and that iteration can be performed unless and until the energy obtained using electron density as a variable, that energy obtained in the last step and in the previous step, if that change is within the limit of error or within the decided limit, then one can say that calculations are complete and system is converged. So that is a basis of doing the DFT calculations. Then pseudo potentials. Pseudo potentials is also a wave function type functions, but they include certain assumptions to hasten the calculations. Then plane waves self consistent cycle, just like HF theory. Then density functional perturbation theory, just used in your post HF calculations. One can say that these are the methods for doing post DFT calculations. So whatever the correlation error is there, that can also be accounted by means of using the density functional perturbation theory. Then basic formalism, first order energy derivative, then atomic forces, second order energy derivative, that is the perturbation theory. Similarly, other methods are also there, but they have been not included in this syllabus. So in this way, one can perform the calculation. Then DFT. Then next one is the semi-empirical methods, and these are the very simplified form of the ab initio methods. In case of ab initio methods, we have seen that electron-electron interactions makes it difficult to solve the Schrodinger wave equation, and in these electron-electron interaction methods, two electron integrals will be there while solving this HF theory or DFT. Two electron integrals are there, and these number of two electron integrals increases if you increase the number of basis functions, and that increases about m raised to 4. That is, if your basis functions are m number of basis functions if you use, then resultant 2 electron integrals will be m raised to 4. That much 2 electron integrals we have to solve in a single cycle. And for optimization, you have to perform 10, 15, 20, sometimes 100 cycles. So you can imagine how much time will be there. So we have to minimize these 2 electron integrals. And what is this semi-empirical method? These 2 electron integrals one can replace by means of some experimental data that is called as a parameters. Some homologous series you can get, take, then evaluate some experimental properties, and then fit that property as a function of carbon atoms or whatever the varying parameter in that homologous series is there, and find the constants and use those constant as a replacement to the 2 electron integrals in the ab initio method. Then whatever the resultant methods are there, these methods are called as semi-empirical methods, and your best example is Huckel molecular orbital theory calculations. Then variation principle is there, secular determinant, secular equations. So this part is that of the old syllabus. But Huckel theory and semi-empirical, these things have been combined together. Then assumptions in the HMO theory, pi electron approximation, how the sigma electrons and pi electrons have been separated, and why pi electrons are used for constructing the wave functions, and then constructing the secular determinant, solving those determinant and obtaining the coefficients, and finally the energy. Then Huckel rule, aromaticity, HMO calculations, prevalence index, that is the reactivity in the organic molecules at a given of a particular atom in a given molecule can be predicted with the help of this prevalence index. Then use of molecular symmetry for simplification of HMO calculation. That is the case if you take the case of benzene or bigger molecules. Then if symmetry is presented, then certain integrals or certain terms can be neglected because they are just a repetition of the other terms due to the existence of the symmetry. So that concept can be used to simplify the calculations and hasten the calculations. The neglect of differential overlap, that is your 2 electron integrals. So those 2 electron integrals one can neglect and replace by means of a additional parameters, empirical parameters. So if we completely neglect, then it is called as CNDO method. If intermediate neglect of overlap is there, that is which part one has to neglect and which part has to be focused on. Then modified intermediate neglect of the differential overlap, then modified neglect of the differential overlap, and so on. Neglect of diatomic differential overlap. So there are 2 electron integrals in the neighboring atom, atoms far away from the atoms of the interest. So if 2 atoms are neighboring to each other, then whatever the 2 electron integrals are there, those 2 electron integrals one can keep, and all other 2 electron integrals one can replace by means of empirical parameters, either experimentally or taken from the theories. So such methods are also there. So based upon how to handle the 2 electron integral, the names have been given for these semi-empirical methods. Then Austin model 1 is also there, that is also called as the PM1 method, parametric method, and parametric 3 method, parametric 5 method, PM6 method, and PM6 is the latest method. Then now current semi-empirical method is PM7 method. Okay, so these methods are there. Comparison in the above mentioned method, comparison in the sense you can calculate the energy. If you have a data for the experimental value, then which method gives you the best results, that comparison you can have either for energy, then bond length, then bond angles, then heat of formation, and so on. Then introduction to various software packages for performing semi-empirical methods. And one of the best and worldwide used tools is the MOPAC. and current version is MOPAC 2016. So that package, and it is freely available for the educational institutes, although it is a commercial for industrial purposes, but for academic purposes it is freely available. You have to register, then you will get that package, and you can show you to your student how to do the semi-empirical calculations with the help of this MOPAC package. And input file again you can generate by means of your freely available tools, that is Avogadro package as well as Gab edit software. You can draw a molecule, optimize that molecule at molecular mechanics level, then generate the Cartesian coordinates or Z matrix, and then give the input keywords with the help of that, and that input file generated can be used with the help of this MOPAC 2016 package, and one can perform this. Also you can use a GAMES package for doing semi-empirical methods as well as ab initio method calculations as well as DFT calculations. It is also freely available. Windows version is also there, Linux version is also there, Mac version is also there for GAMES. Even you can use a GPU based calculations, that is to fasten the calculations, but that thing is little complicated as far as the installation is concerned. Once it is being installed, then your calculations becomes a more faster one. So in this way, one can take into consideration the points which has to be taught to the student, which point has to be given more stress, which has to be given or more weightage, which has to be given to the less weightage, and your student must gets convinced about the significance, importance of this, and then its utility in their future career. That is, if they want to go for the pharma sectors, then also for industrial sectors, then in academic sectors, if they want to go for the research in the material science, then also evaluation of properties using DFT and ab initio is the prime significance in the current research and development, whether they are technological development or academic development. But these are, and after few years, I think it may be a mandatory technique for funding purposes as well as for submitting the research work, whatever the experimental tools you use and whatever the results you get. It may be in the form of spectra, other graphs, or anything. So its interpretation for more complicated systems is very, very difficult, and its final solution is to do the DFT calculations or ab initio calculations for the same systems and evaluate the same property, and then visualize that property on your screen, and then interpret the final result and give the assignment for your spectral peaks or any other thing. That is most important. So some books are there. Those books one can use for the first unit. One can use these two books, even this last book also, third book also. That is first 2 units. Most probably the first unit, that is Introductory Quantum Chemistry by A.K. Chandra, then McCurry Quantum Chemistry. This book is a very, very good book. It contains lots of examples, lot of illustrations, and so on. Then Atkin and Freeman Molecular Quantum Mechanics. That book can be used for the ab initio methods. Ab initio methods. Then this book can also be used for the ab initio methods. This book is excellent one. And one more book is there. I think it is not given in this list. Book Computational Chemistry by Errol Lewars. 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 Computational Chemistry. That book is an outstanding book for ab initio method, basis sets, basis functions, HF theory, their calculations, and so on. Then for density functional theory, this handbook of computational chemistry is also a very good book. Then density functional theory for beginners, basic principles and practical approaches. This, then primer in the density functional theory, this chemist guide. So all these four books are excellent one for DFT calculation, DF standing, for teaching purposes, as well as for learning, as well as for practical training. All these four books are very good. That's why they have been included in this syllabus. So if you have so these are the things that has to be given more weightage while teaching this course, computational or advanced quantum chemistry. बरं, याच्यामध्ये अजून काय अडचण आहे कोणाला?
No, sir. Thank you.
ओके, थँक्यू. कोणाला काय विचारायचं असेल तर विचारू शकता.
ओके, जर कुणाला काही शंका नसतील तर मी आदरणीय दगडे सरांचं मनापासून आभार मानतो आणि डॉक्टर समाधान पवार सर यांना विनंती करतो की त्यांनी पुढील
काय करायचं
गुड मॉर्निंग गायकवाड सर, आवाज येतोय?
येस सर, यू आर ऑडिबल सर, प्लीज कंटिन्यू.
Good morning one and all. Myself Dr. Samadhan Pawar. Here I am going to introduce resource persons of this session. The Professor G.B. Kolekar sir, Shivaji University Kolhapur. Actually he has a very huge CV, but as a formality I will introduce him in very short. He did his B.Sc and M.Sc from Pune University. Then he did his PhD from Shivaji University Kolhapur. Then he has 29 years of teaching experience in college as well as university level. His research is concerned. He has published 152 international and national research papers. Then under his guidance, 13 PhD students have awarded a PhD degree and 4 MPhil students awarded. Then his citation index is 1850 citations. H index is 23. I-10 index is 55. Then he has filed and published 5 patents. Then he also worked in various academic and academic committees in universities, home university and other universities. Then he has completed 5 research projects. His research expertise in synthesis and functionalization of metal nanoparticles and carbon dots for sensing applications. Recently he has published one chapter in Springer National publication. Then he has worked in many. He has worked as a member of organizing secretary in various conferences organized by Shivaji University Kolhapur, as well as he has given many talks in national and international conferences. With this brief introduction, I will request Professor G.B. Kolekar to deliver his talk on revised syllabus on electrochemistry subject. Over to Professor G.B. Kolekar, sir.
Yes. So thank you, Dr. Samadhan, for introducing me in different way. So can you hear me?
Yes.
Okay.
Yes, sir.
Yes. So at the outset, I am very much thankful to the college, Rajashree Chhatrapati Shahu College, who have organized the workshop, such a syllabus. I also thanks his team, especially head of department, Dr. S.V. Patil sir, coordinator, Kishore Gaikwad sir, co-coordinator, Dr. Dodmani, and my friends, principal, Dr. S.T. Salunke, who supported to all these my friends to organize such a wonderful workshop. Today, I am going to just highlight the electrochemistry paper. So those already you might have teach the last academic year also. So more or less the 60% syllabus as we place as it is, those which are already studied or discussed. So some of the articles we have placed in the revised syllabus, so that I will just discuss here. So there are 4 units as earlier whatever we have the syllabus. In similar way, we have carried forward these electrochemistry. So there are 4 units. Unit first, that is actually equilibrium properties of electrolytes. So every unit it is at 15 hours. So first unit, so in the first units, so major we have changed the articles, otherwise unit second, unit third. So as it is, we have placed in the revised syllabus. So in unit 1, while we are going to start to the fresher students, those who are studying the electrochemistry, sir, our intention is to keep just the student should know what is the electrolytes, what is the non-electrolyte, what is the purpose of electrolyte solutions, what are the types of electrolytes are there. So these points we have to mainly focus in front of the students are there. So then he knows that finally the electrolytes, that means one of the substance are there, and when it dissociates into ions in solutions, it acquires the capacity to conduct the electricities are there. So then the electrolytes are there. So sodium, potassium, chlorine, calcium. So this example you have to just give for the students the belongs to the categories in the electrolyte solutions are there. So what purpose? What is the purpose of these electrolyte solutions are there? So it is just the students, we have to give the directions. So actually it is because when salt dissolves, its dissociated ions can move freely in solutions, and then allowing a charge to flows are there. And then they, before going to discuss these, actually the Debye-Hückel theories are there. The student, they realize that these different electrolyte solutions are there. So these different three categories are there. The strong acids are there, strong bases are there, salts are there. So these, the strong electrolytes, they fall into different categories are there. And then we have to go for actually Debye-Hückel theory of interionic attractions are there. And then you have to give just what points we have to focus, what point we have to cover in Debye-Hückel theory of interionic attractions are there. So for this unit first, unit second, unit 3, so better way we have to use the reference book S. Gladstone, Electrochemistry by Gladstone. So this is the best reference book for these 3 units are there. And as per this reference book, when we have to go for this article interionic attractions, the student realized that by explaining the electrolytes, non-electrolytes, then the actually the different types, then the students realize that these, the electrolytes, so that means these different ions are there. That means here for the interionic attractions, that is the Debye-Hückel theory put forth or studied, these concepts are there. So before Debye-Hückel theory for this electrolyte, what he has what he has concerned, the other guys are there. So that Jerams, Noyes, Sutherlands. So these different scientists, different guys have studied the electrolytes, strong electrolytes are there. So what he gives, the attractive forces between ions might have some influence on the electrolyte conductance, and especially with this strong electrolytes are there. And this is considered by these guys earlier, Jerome, the Sutherland, Noyes are there. And then the modern quantitative treatment of this concept is worked by Debye-Hückel theory. And when we have to give, we have to explain the modern concept of this strong electrolyte theory. So the Debye-Hückel has given some postulates are there. So there are different postulates are there. But while studying this interionic attraction, the essential postulates of Debye-Hückel theory, they have suggested. So these postulates, essential postulate of this article, so that we have to focus mainly, that is the postulate is every ion may be considered as being surrounded by ionic atmosphere of opposite sign. So there are different postulates are there, but among the different postulates, so this is the most important postulate, the every ion may be considered as being surrounded by ionic atmosphere of opposite signs are there. And on basis of this postulate, we have to derive one derivation for this Debye-Hückel theory under interionic attractions are there. And for this derivation, so actually most of my friends, colleagues aware that the Debye-Hückel theory interionic attractions, though already studied these points. So, but as per my the intentions or knowledge, while we have to derive these interionic attractions Debye-Hückel theory, we have to show that the final equations, that is psi, that is the potential, which is equal to ZIE by dr minus ZIEK by d. So these equations we have to prove, and for deriving this, obtaining these final equations, the teacher, our community, before students have to go for 3 ways, 3 parts we have to explain the derivations. So first part, so we have to tell to the students to obtain electron density for univalent electrolyte. This is one part. Also, we have to show the electron density for different kinds of ions. The 2 equations are obtained. So for different kinds of ions, the row equation, that is the minus epsilon square psi by kT into summations of ni zi square. And same for univalent electrolyte rho, which is equal to minus epsilon square psi by kT into 2n. So these 2 equations are initially to get. And then these equations, which is placed into the Poisson's equations. In order to solve this potential psi, use the Poisson's equations. And thereafter, to get the thickness of ionic atmosphere, then differentiate, and then finally we get the 2 term in the final equations. So first term, that is the potential at distance r, it is due to given point when there are no surrounding ions, that is Zi by dr. And another term, that potential arises from the ionic atmosphere. So that is the second term. So Zi k by d. So this is the final equations we have to get by giving the postulate Debye-Hückel theory and to derive the interionic attractions for the potential psi equations. So this way, to get or to explain the Debye-Hückel theory of interionic interactions. Now, the second point, that is the actually ionic atmosphere. So in ionic atmosphere, so ionic atmosphere, or that is the time of relaxations, electrophoretic effects. So these are the actually here in the ionic atmosphere. So just we have to give the thickness of ionic atmosphere. So just it is the thickness of ionic atmosphere, just we have to show the relations to be the summations of Ci Zi square, that means concentrations are there. So this thickness of ionic atmosphere, which have some relations, small points are there. Once we have to derive the interionic interactions on basis of this, some the thickness of ionic atmosphere can be explained on connection with the first article. Second, this is the time of relaxations and electrophoretic effects are there. While we are explaining this time of relaxation, time of relaxations of ionic atmosphere, or this relaxation effect or electrophoretic effects are there. So while explain this, so this way, these 2 ways we have to explain this. Define and explain relaxation effect, electrophoretic effect, or simply derive the actually Debye-Hückel-Onsager equation. When we explain this relaxation effect and electrophoretic effect, so this is just simple definition. Explain relaxation effect definition, give his equation. Explain electrophoretic effect, write his mathematical equation. So for example, the relaxation effect, a symmetry of ionic atmosphere, it due to time of relaxations, it will results into retardation of ion moving under the influence of applied field. and this influence on the speed of ion that we call as the relaxation effect. And for the mathematical part, so the relaxation force, we have to give the equations. So similarly, electrophoretic effect, give the explanations and his equations. Once we have to obtain these two equations, so finally we have to derive the Debye-Hückel-Onsager equation. Debye-Hückel-Onsager equation, to equate these two forces, to equate these two effects, relaxation and electrophoretic effects are there, and some small rearrangement. So finally we'll get the Debye-Hückel-Onsager conductance equations, and that equation is lambda, which is equal to lambda 0 minus in bracket a plus b lambda 0 bracket complete into square root of c. So this is well known Debye-Hückel-Onsager equations, and we people have to just intense to the students, tell to the students. So actually the A and B, so these are the constant, that is the A for, that is the because of the electrophoretic, and B, that is the second term, that is for the relaxation effects are there. So simply that Debye-Hückel-Onsager equations, lambda which is equal to lambda 0 minus a plus b lambda 0 into root c. So this relationship is based on the assumptions that dissociations of the electrolyte is complete. So that means this equivalent conductance decreases at appreciable concentrations in terms of decrease in ionic velocity. So this decrease of conductance due to these two forces. That means these relaxations and electrophoretic force. And finally, just give in this final equation, first term in bracket, it is this effect due to electrophoretic, and second term represents the influence of relaxation force. So this is actually the main thing while getting the final equations. So first term, because of electrophoretic force, that means that is the A equations. So A, that is the constant. A and B are the constant. So that constant 82.4 by dt raised to 1 by 2 into n. So this constant B, that is equal to 8.20 into 10 raised to 5 by dt raised to 3 by 2. So this constant, so they are the represents the electrophoretic force and relaxation force are there. So that finally the students has to learn the point from these relaxation force and electrophoretic effect, or just the Debye-Hückel-Onsager equations are there. Now thereafter, once we study the Debye-Hückel-Onsager equations or obtain the derivation, the next point is what are the validity of Debye-Hückel-Onsager equations. How it obeys the Debye-Hückel-Onsager equations. What are the factors influencing these? So this validity, just consider the 2 points to validity of the Debye-Hückel-Onsager equations. For univalent electrolyte, assume the complete dissociations of Onsager equations and consider the two parameters, one for aqueous solution and another for non-aqueous solutions. So for these 2 ways to explain the validity of Debye-Hückel-Onsager equations, then it will be well. So how, say for example, I will just explain the aqueous solution. How will you prove the Debye-Hückel-Onsager equations validities? Now, in order to testing the Onsager equation, consider for the aqueous solutions of few univalent electrolyte. Say for example HCl, NaCl, KCl, silver nitrate. All these are the univalent electrolyte. And while we performing this experiment of the Debye-Huckel-Onsager equation, then finally to show the graph of equivalent conductance versus square root of concentrations. And what we will find here, so straight lines are there. And these straight lines, so while we extrapolate on the y graph, so that is the lambda zeros are there. And from that graph, we try to show to the students, so these graphs for the univalent electrolyte, it is a straight line, and these the univalent electrolytes, the Onsager equations, the values of lambda 0, it is very closely obeyed at concentrations up to about 2 into 10 raised to minus 3 equivalent per liter. When you prepare the concentrations up to 2 into 10 raised to minus 3 equivalent per liter, then and then the Onsager equation is valid. Then and then the straight lines are obtained, and this straight line, on extrapolating on the y graph or y axis, you will see the lambda 0 value for graphical and lambda 0 value for the concerned univalent electrolyte. They are very closely agreed or obeyed. When it happens only, it is only up to concentrations up to about 2 into 10 raised to minus 3 equivalent per liter. So this way, we can say the Onsager equation is valid. So these explanations you have given are all univalent electrolyte. What about the other electrolyte? Say for example, unibivalent electrolyte. And if we prepare the concentrations up to range 2 into 10 raised to minus 3, is it possible to valid? No. The verifications of Debye-Huckel-Onsager equation is more difficult for this concentration. Which concentrations? Those we prepared for the univalent electrolyte 2 into 10 raised to minus 3. So we have to go for the different concentrations. For dilute solutions at 25 degrees Celsius, for calcium chloride and lanthanum trichloride, both cases, they are valid for this unibivalent or unitrivalent or bivalent. They valid when these concentrations to be prepared up to the range of 4 into 10 raised to minus 5 equivalent per liter. That means for the unibivalent electrolyte, the Onsager equations is valid up to the concentrations 4 into 10 raised to minus 5 equivalent per liter. And then you have to say the other bivalent electrolyte. When we plot the bivalent electrolyte, we perform this experiment of Onsager equations, completely shows that discrepancies are observed, not matches with our Onsager equations by plotting the graph of lambda versus root c. Because it is not straight line obtained, somehow it is concave or curve type, like this way will be found. So that means you can say here the bivalent electrolyte are up to this concentrations range, actually it is not valid. So maybe there are different reasons are there. it is just this debile explained here because of these error, so or incomplete dissociations at experimental concentrations are there. So that means for validity of the Onsager equations, we have to go for union validity at different concentration. We have to choose for the unibivalent or bivalent, go for the different concentrations are there. But students should know for this different, the valencies are there, unibi, like this way, 4 into 10 raised to minus 5 concentrations are equivalent per liter. So this is the concentrations range for validification. And for the union valent, 2 into 10 raised to minus 3. So this point is very important for this case. So this is for the aqueous solution. So another validity to be tested for the non-aqueous solutions. Give some more examples to the students for the agreement of these validity of these equations. It is more particularly for the case of chloride, thiocyanate of the alkali metal, the electrolytes such as nitrate, tetraalkyl ammonium. So like this way. So these points, when we consider, and we'll find that the higher valence type exhibit appreciable deviations are there. So these discrepancies, they are observed with the low dielectric constants are there, and perform one of the experiment. So one example given in the Gladstone, that is the conductance of Ki in number of solvents they have been determined, and the various solvents observed Onsager slope and calculated Onsager slope, they are given in the textbook, and the students will be cleared that they actually at still a low dielectric constant with the other electrolytes, the greater discrepancies are recorded. So by observing the graph, by observing the actually table, the students should be clear the points are there. Now so similar somehow these points we have to explain to the students. So actually the Winnie effect, then Debye-Falconi effect. So there are different experiments are there, different electrolytes we have to consider for this, and then we will have give the explanations in this way actually for the electrolytic solutions are there. Now thereafter some Debye-Hückel actually limiting equations are also. So in similar way, the Debye-Hückel equations generally it is tested with the strong electrolytes. So all they are a way to plot some graph of the activity coefficients against the concentrations are there, or consider the KCl, CaCl2, zinc sulfate. So different the valencies, uni or bivalents, and we have give some explanations for this case of this case. Actually, these points we have to all the first, second, or third unit. So you may be refer for this. Yes, Gladstone. Actually, it is given in a nice way. In generally the second unit and third unit. So as it is, we have placed in the revised syllabus are there. So final the topic number 4. So it is the fuel cell and corrosion. So actually this is also the same points, but here we have given the different the type of fuel cell in this topic. What the intentions to give the students actually, the students just should know that the difference in between battery and actually fuel, battery and fuel fuel cells are there. So how does this fuel cell work? So these points to explain before the students, then he knows actually battery and fuel cell and what is the purpose, where they are used, what are the applications, point of view. So this topic fuel cell and corrosions, particularly I am using for the fuel cell for the applied fuel cell, the different types of the cell, that is the hydrogen oxygens, or that is the hydrocarbon air fuel cell. The different types of the cells are there. So these I have collected the points from the Wikipedia, so which is available on our website easily. You can see the recent and the changes, how actually the fuel cell here just it is simply the electrolysis cell, the compartment, the anode cathode electrolysis, oxidations, anode cathode reactions, how they works, and how the fuel which gives the productions of the generation, productions of the electricities, that we have to focus. By there are different types of the fuel cells are there, and every fuel cell gives the electricity or current generations are there, and how efficiency which can be increased by optimizing the conditions for the particular type of cell, that we have to focus for the fuel cells are there. Before going to discuss these types of cell, initially we just explain where the difference between battery and fuel cell, what materials we use for the fuel cells are there, what are the significance, how does work of the fuel cell, and where they are, that is applications parts of the fuel cell. So when we explain these points, then the students should know the different types are there, different guys, different scientists, they develop, they manufactures the different theories, hydrogen oxygen fuel cell, hydrogen air fuel cell, so phosphoric acid. So every type of cell, molten carbonate fuel cell, so alkaline fuel cell, solid polymer fuel cell. So they all these are the functions same, but different capacity, different way, the efficiency are there for the productions of the current or productions of the electricities are there. And then where are they used? That is the part of the applications part. So for this, so better way, the recent all types you will be getting the material on website. So Wikipedia fuel cell, so different way, different material can be collected from the website, and then you people may be getting clear idea about the fuel cell than using the old reference book of the fuel cell. So this is just about the fuel cell. So last point, that is the corrosion. So it is just corrosion points. So we know that we are aware that we are using the corrosions point, corrosions. So it is just related to the industrial point of view. So points are there, corrosions. So corrosions, so it is just simply corrosions, how it appears, what is corrosions, how metal corrodes are there, how they different theories of the corrosion. So it will explain by two theories are there. So that is the dry theory and chemical attack theories are there. So in every theories we have to explain the anode and cathode reactions, and then we'll get how the metals to be get corrode. That is the rate of rusting of iron which is to be obtained. by studying these two theories are there. And after this, so that means here anode cathode, here also anode cathode, and we'll finally get how the rate of resting to be obtained for the examples. So these are the comparison between that means types of the corrosions are there. So thereafter, factors affecting corrosions are there. So there are different factors are there. So we people have to just give the explanations. These rate and extent of corrosions, which depends upon the different factors. Say for example, nature of the metals, nature of the corroding environment. These are the factors which is responsible the how it metal corrodes are there. For example, under the nature of metal, we'll have to give the example by this is actually the electrolysis process are there. So how placing of the positions of galvanic series, how much use of voltage for this procedure. So it depends on the corrosions are there. So then purity of the metals are there. Generally, the rate of corrosion increases with increasing the extent of impurities are there. So in this way, we have to explain the different ways are there: solubility, nature of the surface film, metals. So these are the different parts are there. Say for another part, that is the corroding environment, temperature, it is the responsible factor, humidity of the air, effect of pH, conductance of medium, so many other factors. So few points they are responsible to explain under these points are there. So I think here given nature of the metals and nature of the corroding environment. So under this way to given the factors corroding are there. So type of corrosions are there. So there are different types are there. Crevice corrosions are there, petic corrosions are there, uniform corrosions are there, filiform corrosions are there. So stress corrosions are there. So these points we have to explain the different types of corrosions, how actually it happens are there. So prevention of corrosions. So prevention of corrosions, that means actually I think corrosion controls. So it depends upon the material selection and design. So that points we have to focus under these points. So that means, for example, we have to say one example. If I ask the one example, so choice of the right type of material is the main factor of the corrosion control. So this way we can explain the points are there. For example, noble metals are the most immune to corrosion, but they cannot be used for the economical reason. So in this way, the points which we have to explain under this. So lastly, the corrosion inhibitors are there. So corrosion inhibitors. So here corrosion inhibitors means actually the students should know what is the inhibitors are there. Inhibitors means it is a simple substance. It is a simple substance are there. When such substance add to the electrolyte solutions, they reduce the rate of corrosions are there. So these are the inhibitors are there. So there are different, I think two types of the inhibitors are there. Inorganic inhibitors, organic inhibitors are there. So that means organic material which we can use, add into our system. So it will help to reduce the rate of corrosions are there. So these points in this way we have to explain under the fuel cell and corrosions. So these are actually our intention is to just say, so what way we have to give the message to the students for preparations of the electrochemistry. So whatever the syllabus arranged in these electrochemistries are there. I already explained you for the first unit 1, unit 2, unit 3. We use the electrochemistry by Glasstone. It is best reference book for this. Many other reference book we have cited in the syllabus, but it is best reference book. Yes, class 2, you can use or to tell to students go for this glassstone for these 3 units, and fuel cell corrosion, especially the for recent or applied knowledges collected the materials. You may also search for the online or website material, because this is the recent and advanced the techniques fuel cells day to day, because current generations it is the most important point in comparison in view of the our nation India. We are facing the problem of current or power in rural area. So 10 hours, 12 hours, the load sheddings happen in the rural areas are there. But I have experienced when I was in Korea last year. So I observed, so there, if 1 minute's light, if they are off in the entire nation, so 1 week they are announced to the regions or that places. So 1 minute load shedding is there. So be attention, be careful about that. So such a way, the development of the nations. So because of one, the electricity or current may get developed, the countries are there. But in comparison with this, our India, we have lack of this. So I personally decided to use fuel cell, the old or ready material for the reference book. So recent material, the intention or message cannot be reached or goes to the students. So that I personally decided to collect the material on the website recent types, and I will suggest to the students like this way, and you peoples also agree for my point. So thank you for the apology given by the college. So once again, I thanks the principal Dr. S.T. Salunke and head of the department who have taken the leading to organize such a wonderful workshop, and just we have through this online medium to you. So thank you very much.
Thank you, sir. Thank you very much. If anybody have a questions, please ask. Any question from audience? Okay, sir. Thank you, sir. Thank you very much. Now I request Dr. Anant Dhodmani, sir, to introduce our next resource person.
Okay, thank you, sir. Am I audible?
Yes, sir. Yes.
Okay. Good afternoon, all. Myself, Dr. Anant Dhodmani, Assistant Professor of Chemistry, R.C. Shaw College, Kolhapur. So it gives me a great pleasure to introduce the next resource person of this workshop, Professor Dr. G.S. Gokavi, sir. Currently, he is working as the head of the Department of Chemistry, Shivaji University, Kolhapur. Since he completed his M.Sc. and PhD degree in physical chemistry from Karnataka University, Dharwad, he started his academic career as a lecturer in Department of Chemistry, Shivaji University, Kolhapur. He has the more than 30 years of teaching and research experience, and hence he published more than 100 research publications with journals of international repute. Under his guidance, awarded more than 20 PhD scholars and more than 5 MPhil research scholars. Also, currently, he also looking for various bodies of the Shivaji University Kolhapur in the field of academic, research, and administrative professions. Hence, now I request Professor Dr. G.S. Bokavi sir to deliver his talk. Thank you. Bokavi sir.
Yes. Let me open my
Please
this
start.
one. Okay.
Okay.
Molecular structure 1. Is it visible?
Yes, sir.
My presentation, is it visible to you?
Presentation is not visible, sir.
No, sir, it's not visible, sir. Kindly share it through screen share, sir.
Okay. Okay, now I think it is visible.
Yes, sir.
Okay.
Okay, sir. Visible, sir. Start.
Okay. Thank you. So today I will be dealing with molecular structure. In that, the unit 1, that is the introduction to the interaction of electromagnetic radiation with matter. We generally come across various spectra. I have just collected some of the spectra. See, we have visible spectrum, we have IR spectrum, we have the microwave, and another one is the NMR spectrum. I will come back to it, but this is the nature of the spectrum we generally deal with, and it is the physical people who can explain theoretically very well about the nature of these spectra obtained. As far as electromagnetic radiation is concerned, we will come across two variations. One is the electric field variation and another is magnetic field variation. Both are perpendicular to each other. That's why the name electromagnetic radiation will be given to that. So therefore, as far as the electric field variation is concerned, that will be attached to the electrical properties of the molecules. And as far as magnetic field variation is concerned, which is perpendicular to the electric field variation, that will be concerned with the magnetic properties of the molecule. To name some of the electrical and magnetic properties of the molecules, so dipole or polar nature, polarity of the molecule will come across that electrical field variation. And as far as the spinning of the atomic particles and atomic particles is concerned, that comes under which generates an electric and a magnetic field, which generally we consider it as a bar magnet, which is in case of NMR. So that comes under the magnetic field variations, which it has been represented by the electromagnetic radiation. Radiation which is in the form of wave, can be represented in various different ways. That is, this is the waveform of the electromagnetic radiation, which can be represented in various waves. The first example, that is, this is omega represents the angular velocity, and A represents the amplitude of that one. Okay, so in terms of angular velocity and time, it will be represented by y is equal to a sine theta, or a is equal to sine omega t. As far as theta is concerned, the angle made between the traveling wave and some reference direction. So this is the theta angle, and a is the amplitude. So in terms of theta, or in terms of angular velocity, you can represent it by means of either a sine theta, and theta is equal to angular velocity into time. So that gives us omega t. So this is the one way of representing the electromagnetic radiation. If P is the time required to complete one cycle of that radiation, which is been represented in the circular form here. Okay, if you follow the wavefront and represent it in terms of a circular form, you can come across such type of representation. And this P means the time required to complete one cycle. Okay, if you start from P, that can be represented by means of omega or 2 pi cycles. That is the time required to complete. If omega is the velocity, angular velocity, and 2 pi is the total area of that this one. So this would be circumference of this one. So this will give you the time taken for to completion of one complete cycle. So in terms of that, if you want to represent theta replaced by this one, it would be 2 phi omega 2 phi nu into t, where nu is your frequency. Okay, nu is the frequency of that wavelength. And the displacement can also be replaced. Displacement means the wavefront, the displacement of the wavefront from the some reference point, that can be represented by means of its velocity into time. So x is the displacement. In terms of displacement, you can represent the equation by means of 2 phi nu x by c. So these are the various forms. And also we generally come across wavelength, which wavelength is represented by means of the distance between two crest or two this one. So this wavelength, you can also represent wavelength by means of c over nu, and the wave nature of the electromagnetic radiation in terms of wavelength can be represented by this equation. A is equal to sine 2 phi x divided by lambda. So any one of these forms can be used to represent the electromagnetic radiation. So in summary, you see angle, if you represent it by means of angle, it would be y is equal to a sine theta. If it is angular velocity, it would be omega t, a sine omega t. If it is frequency, it would be represented by means of y is equal to a sine 2 phi nu t. And if it is distance or displacement, you can represent it by means of 2 phi nu x by c. And if it is wavelength, you can represent it by 2 phi x by lambda. And another one which we generally come across is the wave number, which is the reverse of or 1 over wavelength. So that is called generally wave number. Even in terms of wave number also, we can represent the radiations. Some of the examples. The molecule quantization of the energy. A molecule can have various types of energy, starting from rotational, vibrational, electronic, and other forms of the energy. This molecule exists in several discrete energy levels. So discrete energy levels in the sense, as Dr. Dagade might have explained it to you, that is, energy cannot have any random value, so it can have only discrete value. So discrete energy levels, so therefore when the energy levels are of having discrete energy levels, the difference between them is also fixed. So when that difference is taken, that is delta E is taken, that will be reverted to the frequency by means of the equation, that is delta E is equal to H into nu. And if you convert the frequency into energy or energy into frequency, this equation can be used for that purpose. So the relations delta E is equal to H nu can be used to represent the difference in the energy levels where the transition between higher and lower energy levels occurs in case of interaction between the molecule and the electromagnetic radiation occurs. That can be represented by means of this equation, either in terms of frequency or in terms of energy. So that is represented here. That is, if it is in terms of energy, it would be expressed as joules, and if it is in terms of frequency, it would be expressed as hertz. And even in various forms also you can transfer that into, depending upon what type of the spectroscopy you will be dealing with. Then the molecular, what you call it as molecular motions, which are expressed in terms of either vibration or rotation. In this case, I have taken only the two examples, vibrations and rotations. You see, a polar molecule having its dipole, having a positive charge on one atom and a negative charge on another atom because of the redistribution of the electron density around that particular molecule. So that will be having, that is called as a dipole, and dipole will be having a particular direction as represented by towards the arrow towards the negative charge. So this dipole, if you see, when it rotates clockwise, the positive and negative charges will go on also rotating. So this dipole with the arrow has been shown by means of this arrow will change its direction. See, the arrow is towards the downwards, and now it is towards the left hand side, and now it is towards the right hand side. So if you follow the head of this arrow, okay, arrowhead of this one dipole, see, and if you join the arrowheads, it will be in the form of a wave. So this wave nature of a rotation, because of the rotation of a dipole, okay, so if this matches with any of the electromagnetic radiations, then their exchange takes place, and then this molecule will exchange energy with that, and it can be excited to the higher energy level. So because of that, either the absorption, and when it comes down to the ground state or the original state, then it will emit the radiation. So such type of interactions will lead to generation of a spectrum, and now we are considering the rotation of a dipole here. So I think that results into a rotational spectrum. Okay. Next one is vibration. You can consider in the similar manner. This is the another one, that is HCl. This we have considered it as this is a general molecule, and the example of that one is HCl. And this is the vibration, CO2. CO2 as such, you cannot classify it in terms of as a polar molecule. Okay. So because the electron density of both the electron negativity of both the oxygen atoms are same, so therefore it would be equally distributed. So you can call it as a non-polar. So in case of non-polar also, when during the rotation, it may not be resulting into any wave form of nature as far as rotation of this molecule is concerned. But as far as vibration is concerned, you can see when it touches, the bond between carbon and oxygen touches, okay, asymmetrically or symmetrically. So then what happens? The dipole nature of the molecule also goes on changing, which is represented here. So the direction also goes on changing. If you join the arrowheads of this molecule, which is represented as means of an arrow, okay, so that also results in the form of a wave, and this also interacts with this one, and now such type of interaction will lead to a vibrational spectrum. So therefore the molecular motions like rotation or like vibration will also generate a wave type radiations, or it can interact with the wave type radiations, and that results into either the rotational spectra or the vibrational spectra. Then width intensity of spectral transitions. So width intensities, as far as the examples which I have shown it initially, see, you have a little bit broader K-4 spectra as far as visible is concerned, visible spectrum is concerned. If you come across this one, you see a sharp lines are present in case of NMR is concerned. And in case of IR, if you consider that of the OH stretching, it will be a very broad signal. Okay. This is in terms of transmission, and whereas this is in terms of absorption. So therefore, such type of difference spectra are obtained, and that is because of the intensities and the width of the spectral transitions. So the broadness of the peaks can be narrowed, I think this. So if you see the nature of the spectrophotometer or the structure of the spectrophotometer, you will have two slits. One is the where the energy radiation enters into the sample, and another one where the energy comes out of the sample. So when it enters, it also passes through a slit. Okay, if you call it as a S1 slit. Let me see whether I have the spectrum. No. So that slit would be having a certain dimensions which you cannot go below than that. So therefore, that limits your intensity, width of the intensity spectral transitions. So that you have maximum, this one can be obtained by means of calculation depending upon the uncertainty principle, which I will show you later on in one of the examples. Then collisional broadening. As far as collisional broadening is concerned, except in case of gaseous state, I think in solution state and in the liquid state, to some extent in the gaseous state, each molecule will be colliding with each other. So because of the collisions, some outer energy levels would be having some changes, a minor changes. Okay. So that minor changes will lead to the change in the energy also. So that energy change, which is very small in nature, cannot be noticed otherwise, but in case of spectra, it would be noticed. And that you can understand by means of the distribution, that is Maxwell-Boltzmann distribution, in case of velocities, if you consider, or otherwise also. So the distribution is not a very sharp line. It will be having a very broad peak. So that broad peak indicates that collisions are occurring even in case of liquid and gaseous states. So because of that, the changes in the energies of the outermost electrons or outermost energy levels, that leads to some changes in the outermost energies because of the compression and expansion of the energy levels to a little extent. So that will be leading to the broadness of the spectrum, which I think it has been noticed in case of UV visible and IR spectrum. I will come to it later when I deal with this one. And Doppler broadening is also same thing. That is when there is other influences are there. For example, nearby you have a dipole molecule, or you have a non-polar molecule, or you have a polar molecule. So that type of the influence of such type of molecules on the energy level outermost electrons will be giving such type of changes. So Heisenberg uncertainty principle, which tells you that the uncertainty in energy and its product with uncertainty in time is equal to, approximately equal to H over 2.5. That comes out to be 10 raised to minus 34 joules. Okay. From this, you can calculate the uncertainty in the either the energy or the this one. So example which I have taken it here. The wavelength of radiation during absorption, particular spectroscopic transition observed 10 micrometer. Express this wave number and calculate the energy during this corresponding radiation. This is the conversion of radiations, lifetime, I have not taken any example of this. Then comes to the intensity of the spectral lines. Intensity of the spectral lines depends upon transition probability. This is basically require the selection rules for that. What type of transition is allowed, what type of transition is not allowed, and population of the state. This is also one of the important one, which we can, with the help of this one, we can explain the nature of the NMR spectra. If we have two levels from which the transition to the third are equally probable, then obviously the more intense line will arise from the level which is initially having the high population. This can be very easily calculated by using the Boltzmann law. If we have two energy levels, one is the lower energy and the upper energy, and the difference between them is delta E, then you can use the Boltzmann distribution law, where K is the Boltzmann constant and T is the temperature. The ratio of N upper to the N lower will be given by this in terms of energy difference between those two upper and lower energy levels. So on that basis, this example has been given. So a frequency, okay, conversion. This is the frequency, population. I don't know whether I have taken it as well. We can consider this one. Delta E is considered to be 4.0 into 10 raised to minus 22 joules per molecule. And as far as our law is concerned, this one depends upon delta E and temperature. Okay. Now let us see what happens when delta E is kept constant. If you increase the temperature from 29K to 2900K, you see number of molecules present in the lower state goes on decreasing, and number of molecules present in the higher energy state goes on increasing. So therefore, if we increase the temperature, the population of higher energy state goes on increasing. So similarly here also another example is given. This is about the stability of the molecule in the excited state. Now coming to this one, if you go on increasing this delta E, keeping the temperature constant, if you go on increasing delta E, this number of molecules in the ground state goes on increasing, because the molecules will not be having enough energy, enough thermal energy to jump into the higher energy state. If they jump into the higher energy state, there is no necessity of absorbing radiation. But now, if you go on increasing the energy, then what happens? The number of molecules present in the ground state goes on increasing. If you go on decreasing the energy, then the number of molecules present in the ground state goes on decreasing. And a state will reach if the energy is so much less that if we have two states, N1 and N2, N1 is the lower energy state, and number of molecules in the lower energy state and number of molecules in the higher energy state, they become equal, almost equal. The same thing happens in case of your NMR spectroscopy. In case of NMR spectroscopy, if we have 2 lakhs molecules present in total sample, then what happens? Less than 1 molecule to 1 lakh will be present in the higher energy state, and 1 lakh 1 molecule will be present in the lower energy state. So when you expose such a molecule which can be noticed only in presence of an high field magnetic strength, high strength magnetic field, then these two energy levels are splitted. So the lower energy will be having 1 molecule extra than that of the higher energy level if the total number of molecules present in the sample is 2 lakh. Now what happens if such a less population which is present in the lower energy level, then when we expose it to a frequency, radio frequency, then only 1 molecule will excite to the higher energy state. And when only one molecule will excite to the higher energy state, you see, here I have considered nearly about 10 raised to minus 22 joules per molecule, which is considered to be a very high one. But in case of NMR, this goes on decreasing. So when this decreases, you can imagine how to detect so much of less energy as far as in a spectroscopy is concerned, because most of the spectrophotometer, when they come out of the sample, radiation comes out of the sample, it will be detected by means of a photocell. So photocell, in the sense the radiation will be falling on that, it will be converted into electricity, and then electricity will give you the signal. But now in this case, in case of NMR, it is just impossible to identify. Even if you consider 10 raised to minus 22 joules per molecule, only one molecule, okay, only this much of energy cannot be exposed to the photocell cannot be exposed to the such a smallest energy, and it can be converted into current. So what happens in case of NMR spectroscopy? The molecule from the ground state will be excited to the higher state, only one molecule, and again it will be allowed to come down because the energy is very less. It will easily emit the energy by means of collision. In case of either there are two ways of losing the energy as far as NMR is concerned. Because of those two ways, it will come down. Okay, so when it will come down, again you will excite it. So this process of exciting and emission, excitation and emission will continue, and the energy required for that will be stored in computer, and later on the total energy will be withdrawn in the form of a signal. So when such thing happens, you see only one molecule, the total spectra or the energy difference is concerned with only one molecule. Whatever the changes, that is collisional broadening and the Doppler broadening, which we have discussed earlier, that will be concerned only with the one molecule, which is a constant one. So because of that, you will get the signal corresponding to only one energy, single energy, not a distribution of energies. So because of that, the signal comes out to be single one. See this. So this corresponds to only one proton, which is present in this one, lower energy state. So, but whereas this comes out to be Avogadro's number of molecules which are present in case of IR spectra or UV visible spectra. Okay, so because of this one, the uniqueness of spectrophotometer, NMR spectrophotometer or the NMR signal is because of that one. That is the Maxwell-Boltzmann distribution law. And even you can relate that Maxwell-Boltzmann distribution law to the cost of the instrument also. UV visible is supposed to be a lesser cost, but whereas highest is NMR. Even it can go up to 4 crore, which depending upon the frequency you choose. Okay, so this is the difference between the main spectra, and the spectrum differences is because of the simple law which we have already learned, but we are not concentrating on that. This one, so that is your Boltzmann distribution law. This example, this one. So this is about the initial into the electromagnetic radiation. Now I'll just briefly give you an idea about the second part of it. The microwave spectroscopy. Is it visible?
Yes, sir.
Yes, sir, it's visible, sir.
Okay. As far as microwave spectroscopy is concerned, which we have already discussed, it's a rotation of the molecules. It's about the rotation of molecule. And when the rotation comes into picture, I think you will have a rotational axis, and the moments of inertia, which is more important as far as the quantum mechanical considerations of the rotational energies of the molecules are concerned. So therefore, along with the principal axis of rotation, the moments of inertia can be represented as IA, IB, and IC, which is shown here. This is IA, IB, and IC. So the principal axis of rotation. Around that, if three perpendicular axes are considered, you will have three moments of inertia for a principal axis of rotation. One is IA, another one is IB, and third one is IC. Depending upon the values of these three moments of inertia, you can classify the molecules. So the linear molecules will be having, that is, three directions of the rotations about the bond axis, okay, in case of linear molecules. So about the bond axis, the rotation will be resulting into zero moment of inertia, but whereas around B and C, you will have both are equal in nature, equal in magnitude. So that is, the moment of inertia around B axis and moment of inertia around C axis would be equal. So if this is the characteristics of the moment of inertia around A, around B, and around C, IA is equal to 0, moment of inertia is equal to 0 around A and around B and around C. If both are equal in magnitude, then such type of molecules can be classified into linear molecules. Next is symmetric top molecules. So the condition for symmetric top molecules, depending upon the same three moments of inertia which we have defined in case of linear molecules, that is IB is equal to IC and not is equal to IA, same as that of the this one, because even in earlier case also you can consider the same equation, IB is equal to IC, but these two are not equal to IA. No doubt IA is 0. So if IA is also having certain value, then such type of molecules will be classified into symmetric top molecules. And you will have, depending upon the value of IA, whether it is greater than IB and IC, or whether it is less than IA and IB and IC. Then if it is greater than IB and IC are greater than IA, then that type of molecule is called prolate symmetric top, and IB and IC are having the less value than that of IA, it will be calling symmetric top molecule. The examples in case of prolate type is methyl fluoride, and example in case of oblate type is boron trifluoride. Boron trifluoride is a planar molecule, but whereas methyl fluoride is not a planar one. Then spherical top molecules, if all of them IA equal to IB is equal to IC, then such type of molecules are called as spherical top molecules. Example is methane. Asymmetric top molecules, where all the three will be having the asymmetric top molecule. I think all the three will be having all the moments of inertia. There, I think some correction is to be made here. So all the moments of inertia are to be different. The example is water and vinyl chloride. So this is the classification of molecules according to the moments of inertia, values of the moments of inertia. Rotational spectra of diatomic molecule. So rotational energy, like any another energy, form of energy, is also quantized, and only the permitted energy levels will be present in case of rotational energy according to the Schrodinger equation. Okay. So we'll just consider a simple diatomic molecule. So simple diatomic molecule, and we'll assume that the distance between M1 and M2, where M1 is one atom with mass M1 and M2 is second atom mass M2 in a diatomic molecule which we have considered, and the bond length between M1 and M2 is supposed to be constant during the rotation. That is our assumption. So it means that the bond which we are considering here between M1 and M2, which are two atoms of a diatomic molecule, so that bond length is rigid one. It will be just like an iron rod. So that is the assumption which we made it here. Okay. So R0 is the equilibrium bond instance, and if you consider C as a center, if C is the center of gravity of these two, this molecule, okay, where the equal mass distribution occurs, then around C or about C, the distance between C and M1 is R1, and distance between C and M2 is R2. So that at the final R0, that is the equilibrium bond distance, is equal to R1 and plus R2, which is expressed here. So the condition of center of gravity means equal distribution of the masses. So that would be M1 into R1 must be equal to M2 into R2. So this is the condition of M1 R1 is equal to M2 R2. So combining these two equations, that is, this is the equation for a bond distance and this is equation for a center of gravity. So if you combine these two equations, then you can come across, or you can solve it in terms of the R1 and R2. The moment of inertia, the definition of moment of inertia would be M1 R1 square and M2 R2 square. I will just split this one. That is R1, I will consider it as R1 R1 and R2 also R1 R2. R1 R2 R2. So M1 R1 R1. So this part I'll just exchange it with M2 R2. This part I will exchange it with M2 R2 as far as the center of gravity equation is concerned, and this part I will replace it with M1 R1, so that the resulting equation would be this one. So where R1 R2 are common and I have taken it outside, so it would be M1 plus M2. So M1 R1 is equal to M2 R2 and M2 is equal to R0 minus R1, that is this expressed in terms of the bond, the first equation. So now, so M1 R1 is expressed in terms of the bond distance. Similarly, you can express R2 in terms of the bond distance, whereas M1, M2 are constants as far as once the atoms are defined. So R1 is expressed in terms of bond distance, R2 is expressed in terms of bond distance and the respective masses. So the moment of inertia equation, now this equation becomes M2 R0 divided by M1 M2, that is R1 is equal to M2 R0 divided by M1 plus M2 into M1 plus M2. Okay. So M1 R0, that is R2 is equal to M1 R0, M1 plus M2 and whole thing divided by M1 plus M2. So M1 plus M2 in the denominator and in the numerator will get cancels with each other, and you will have this expression, and this total mass containing expression M1 M2 divided by M1 plus M2 is called as the reduced mass. So a simple equation for moment of inertia in terms of reduced mass and the equilibrium bond distance would be R0 square, mu R0 square. So in terms of this one, Schrodinger equation will be expressed as, in terms of joules, the energy of a rotational energy will be given by S square divided by 8 phi square I is the moment of inertia, J into J plus 1, J is the rotational quantum numbers, can have values from 0 onwards. Okay. So the moment of inertia which here we have expressed, since we are considering a linear diatomic molecule, we will have either IB or IC, because IA would be equal to 0. So therefore, IB or IC, anything can be considered. Generally, they consider IB. Okay. So in terms of wave numbers, you can divide it by means of HC, then you will get this expression, and this you can keep it as B as a rotational constant. So simple form in terms of wave number as far as rotational energy is concerned, rotational energy in terms of wave number is equal to B into J plus 1. B is equal to H divided by 8 phi square IC, which is called as the rotational constant. Okay, in terms of centimeter inverse. Now the allowed energy levels, that is, it can have 0, 1, 2 and onwards. So for J is equal to 0, energy would be 0 as far as this expression is concerned, because if you multiply anything with 0, it would be 0. So the J is equal to 0, it doesn't have any energy. And for J is equal to 1, the energy would be 2B. For 2, it would be 6B. For 3, it would be 12B and so on. So these are the energy levels and these are the values. And selection rule for this would be delta J is equal to plus or minus 1. And so therefore, the difference between any two energy levels of this one, so this would be 2B, this would be 4B, this would be 6B, this would be 12B and so on. So that difference, if you calculate by using this expression, okay, J is equal to J plus 1, you will have 2B into J plus 1. So if you substitute J is equal to 0, then it would be 2b, because j is 0 is the starting point of this one. So this is 0, 2b. If you put it j is equal to 1, it would be 1 plus 2, 2 into 2, 4b. Like that, see, from 0 to 1, it would be 2b, 1 to 2, it would be 4b, 2 to 3, it would be 6b, and so on. So if you start from 0 level, 2b is the first line, 4b is the second line. The difference between these two is 2b. 6b is the third line, and difference between second and third would be 2b. So you will have equidistant lines placed as far as the rotational spectra is concerned. Okay. Application of rotational energy, rotational spectroscopy. That is the only unknown thing which we know, which we can calculate or which we can determine experimentally, is that B. So B contains H, 8, 5, and C. All of these are constants. Only I can be calculated with the help of that one. That is, if you know rotational constant experimentally, you can calculate the moment of inertia. If you know moment of inertia, you can calculate the rotational constant. Okay. So the moment of inertia, even masses are constant, so that cannot change. If the atoms are defined, masses will also be defined. So mu is fixed, and what you can calculate is the equilibrium bond distance between, or the bond length of a particular molecule. Okay, so that is the application of rotational spectroscopy. So some of the examples, that is the B value is given and bond length is supposed to be calculated. So if the B value is this one, bond length comes out to be 1.095 Armstrong units. Okay. So similarly, if you know the bond length, you can calculate the B value. So if the bond length is 141 picometers, then B comes out to be 848.52 per meter, or 8.4852 centimeter inverse. Okay. So if B is calculated, you can calculate the other transitions, values of the other transitions also. So like that, you can calculate intensity of the spectral lines. As I told you, intensity of the spectral lines means the line or the transition which is occurring from the highly populated rotational energy level, that gives you this one. So to decide about highly populated energy level, I think you have to consider the degeneracy of the rotational energies. So degeneracy of this is again the Boltzmann distribution law. So the intensity of the spectral lines goes on decreasing as far as our degeneracy is not considered. If you consider the degeneracy, okay, degeneracy of the energy states, degeneracy, if you consider from, or if you calculate it from by means of angular velocity, okay, so the angular momentum and then its relation with the energy, if you calculate, it will be having 2j into j plus 1, 2j plus 1 energy levels. That is, degeneracy is 2j plus 1. So that splitting of the 2j plus 1, you can consider, if this is the value of j is equal to 1, you will have 3 energy levels again splitted. That is, this is for plus 1, minus 1, and 0. If you have second one, you will have 5 energy levels. So therefore, if j is fixed, then you will have 2j plus 1 splitting of the energy levels, which are having equal energy, but their direction of the rotation would be go on changing. So these are the degenerate rotational energy levels for j is equal to 1 and j is equal to 2. Okay, and the magnitude of that comes out to be square root of 2 in case of j is equal to 1 and square root of 6 in case of j is equal to 2. So because of that one, if you consider the 2j plus 1 degeneracy of the rotational energy levels, then the population, if you plot it, earlier we have plotted it simply, see, this Bj Hc by Kt, so this goes on decreasing starting from j is equal to 0 value, but if you consider the degeneracy also, you can see it will have a maximum somewhere in between. Okay, so this is for 300K, and as the temperature goes on increasing, as I told you, the higher energy levels goes on more and more populated. So this maximum population has been shifted. Maximum population at 300 Kelvin has been shifted to this value of J at 1000 Kelvin. So this is the nature of the population of energy states, rotational energy states, as of if we consider the degeneracy. So the transition from J is equal to 0 will not be highly populated. So it will be somewhere around 2 and 3. Okay. So therefore, the line starting from the transition line starting from energy level 3 would be having the highest intensity. That's why the spectrum, rotational spectrum, would be having a maximum in their nature. Okay. So that is this one. See this one. So the population goes on increasing because of the degeneracy. The highest population which comes out to be in this example is J is equal to 7. So the line obtained from the transition of J is equal to 7 is highly intense. Intensity of spectral lines. Then you can also calculate the maximum population, the value of J, where the population is maximum by means of this equation. J maximum is equal to square root of KT into HAB minus half. So from this you can obtain the rotational energy levels, quantum number of rotational energy levels, which is having highest population for a given B. So isotopic substitution, again, it will also go on reducing the energy levels, because in case of the rotational spectra, explanation for the rotational spectra, we have so Bj into J plus 1, Bj into J plus 1, and this B contains, see this expression, energy for rotational energy will be Bj into J plus 1. J is a quantum number. As far as B is concerned, it will be having H divided by 8 phi square IC in terms of centimeter inverse. I contains again mu R square. So mu contains M1, M2 and M1 and M2 in case of diatomic molecule. If any one of M1 or M2 goes on increasing, then I goes on increasing. When I increases, B decreases. So when B decreases, the energy of the rotational energy decreases. That's what it has been represented here. See, if 12 CO, because M1 in case of CO, where this spectrum has been calculated, so it was 12. But when the molecular atomic weight of carbon increases to 13, the moment of inertia goes on increasing. Since the moment of inertia increases, the B value goes on decreasing, because moment of inertia is in the denominator of B expression. So therefore, the energy levels, difference between the energy levels goes on decreasing. See, this goes on decreasing, and spectrum also will be little bit having decrease in separation between the lines of the spectrum. Okay, this is the effect of isotope. And when you consider the non-rigid rotator, I will just give you a table for that, then you can understand. See, from J is equal to 0 to 1 transition, if you calculate from the B value, okay, that is, this is the B value for J is equal to 0 to 1 transition, 20.56. If you calculate the bond length of that one, it comes out to be 0.0929 nanometers. Then I will jump to the J is equal to 10 to 11 transition. You see, the same bond length has been increased to 969. So it means that if the number of rotations or the rotational energy goes on increasing, because of the rotation, the bond will be stretched. So it doesn't remain rigid. This calculation shows that our assumption in case of rigid bond length or rigid bond has been totally not accepted, because the bond length goes on increasing. If you can see from the first row of this one, the value of bond length in the first row, which is 929, it has been increased to 969, which is a considerable increase as far as the distance is concerned. So this is here, because of the rotation, if you consider this as a rigid one, but here it has been increased in the sense, along with the rotation also, the bond or the molecule vibrates. So that also has to be considered. So that effect again leads to decrease in the energy levels. See, if it is a rigid rotator, and there will be decrease because a term, extra term has been added because of the non-rigidity. That is, this is the distortion term. So d j square into j plus 1 whole square, and this is a negative term. So therefore, although d is very small, but since negative, in the sense small decrease would be there initially, and then later on, since it is j square and j plus 1 whole square, it goes on amplifying. So therefore, the difference between the energy levels goes on decreasing if we change from rigid rotator to non-rigid rotator. So these are the some problems, and you can calculate from that expression. I will just want to say something here that see, we have considered a diatomic molecule. So for diatomic molecule, in order to solve that, see, diatomic molecule, diatomic non-rigid molecule. Okay, you will have two unknowns. If it is a simple rigid one, you have only one unknown B, but now you have two unknowns, that is D, distortion constant. So therefore, to solve two unknowns, you require at least two equations. So that's why three wavelengths have been given here, three wave numbers have been given here, okay, for the consecutive transitions. So from that, you can calculate the B value. So from these wave numbers, you can get two equations containing B and D, and then later on you can solve them so that the value of D can also be obtained. See, this is the D value, 3.7 into 10 raised to minus 4 centimeter inverse. D value is very less as compared with B. B comes out to be B, average B, if you consider, it would be 8.4, but whereas D comes out to be 3.7 into 10 raised to minus 4. So this is a very small value, but it leads to more difference when the J value goes on increasing. So as far as polyatomic molecules are concerned, now as far as polyatomic molecules, for a diatomic molecule, we already have B and J. As far as polyatomic molecules are concerned, we have another one, that is now here we are introduced with another bond length, because polyatomic molecule, even if you consider the triatomic molecule like linear molecule like OCS, you must have minimum two equations to solve for the bond length and then go on solving them. So this is the example which I have taken, again by some mathematical means. You can calculate and you can come across the final expression, that is for a polyatomic triatomic molecule, okay, X, Y and Z, the moment of inertia can be expressed by this expression, or you can also express it by means of this expression. Any one of these two can be used. Okay, so by using that, you can calculate the B value, or otherwise, if you know the B value, you can calculate moment of inertia, and from this moment of inertia, you can calculate YZ and XY. So these two bond lengths can be calculated with the help of this one, simultaneous equation solution. That I have solved it here. Another example which I have taken it from this one, your Atkins, pure rotational Raman spectra of gaseous benzene and deuterated benzene yield the following rotational constant, C6H6. It comes out to be B for benzene comes out to be 0.18960 centimeter inverse, And for deuterated benzene, it comes out to be 15681. See, decrease in the B value because of increasing the atomic weight of one of the atoms. Okay, the moment of inertia for C6H6 and C6D6 is also given like this. So when you solve this, for solving this one, it has been just, the solution is also given in case of Atkins, in a manual for Atkins. Okay, so from there I have taken it. So if we represent these bond lengths, that is CC bond length by means of RCC, this is the RH bond length, that is, this is the principal axis, C6 axis of rotation. So the RH, that is this bond length, these two H atoms, if you join these two atoms, it will join. So the distance between the line joining these two H atoms and the C6 axis, that I represented by means of RH, and the same thing with the line joining two carbon atoms, that I represented by RC, and the bond length which we are interested is RCC and RCH. Okay, so this can be calculated, that is, you solve it and calculate the value of RH. Okay, RH can be obtained and RC can be obtained. RH is here and RC is here. So from RH and RC, you can then solve it. RCC is equal to RC divided by cos 30, and RCH would be RH minus RC by cos 30. So like this, if you solve, then you can get the RCC value as 1.396 into 10 raised to minus 10, and RCH as 1.085 into 10 raised to minus 10. Okay, this is another example of triatomic molecule, OCS, solved in another way. Even you can solve for such type of molecules, N14, 14, 16, N14, 14, 18. Okay, where you will get the bond length of NN and NO. So this is about the molecular spectra, and in that microspectroscopy, I hope you can understand the time limitation. So if you want any help, I think I can share with you even in future also. So if you want any questions, then you can ask me.
Anybody have a questions from audience? I think no questions, sir.
Okay.
Thank you very much, sir, for your kind guidance. I request all the participants, you please join once again at 2 o'clock. Thank you. Thank you very much.
Thank you.
This is actually a lunch time. It's a lunch break. So you may leave the meet and you can again rejoin at 2 o'clock. Thank you very much once again. घेतो घेतो. पलीकडे धोडमणी सर म्हणून आहेत. एक मिनिट.
गायकवाड सर हो सुरू करा की गायकवाड सर.
एक मिनिट सर, सरांना मी होस्ट करतो. एक मिनिट सर.
हा गरडकर सर दिसतात.
पॅटर्न हे आता आपली तिकडे हे पण टाकायचं असते पॅटर्न पॅटर्न म्हणजे महत्वाचे संस्थेचे विद्यापीठाचे
हॅलो
शिंदे सर
सर ओके
हा सुरू करा.
आवाज येतो का खरं सुरू करायच्या अगोदर?
येतोय सर.
येतोय सर.
बर
हा येतोय.
Good
पार्टिसिपंट फक्त 20 आहेत.
Good afternoon to all. Now the second session will be continued after lunch. Just now, Honorable Professor Dr. Garadkar sir has joined. I request my colleague Dr. Sri Ram Shinde sir to please introduce our today's resource person. Over to you, Shinde.
Dr. K.M. Garadkar sir is Professor of Physical Chemistry in Department of Chemistry at Shivaji University, Kolhapur. He has a teaching experience of more than 25 years, considering the research guidance for PG, M.Sc. projects, more than 150 projects under his guidance. More than 6 students have pursued the MPhil, and many students have pursued the PhD. More than 100 publications and more than 25 conferences.
More than 200, Shinde.
Yes.
More than 200.
More than 200, sorry, okay. More than 200 publications. I have taken the biodata, sir, okay. Invited
So 100 is a very small number.
Sorry, sir, I have taken from online, that's why Google.
No, online is more than 200. Okay.
Okay, sir, sorry.
So as to see, so my point is, okay, the teacher is it is not just teaching for students. He must be well aware with also research. So that's why it is very better to give the biodata with research also. Okay, continue.
Yes, and more than 2,000 citations yes, cited.
More than 4,000 citations.
Okay, sorry, sir. So he has a very
So this
great
is also
biodata.
qualitative index of a
great,
teacher.
We have a great opportunity that such a eminent personality that today we have. Thank you, sir. Thank you.
Okay, Dr. Sinde, thank you. Not Dr. Mr. Sinde, thank you for your introduction. Okay, so first of all, I would like to say very good words regarding conduction of this kind of activity. So it is very essential. So because at university level, we will do the syllabus, we will frame the syllabus. And typically for college students, it is very difficult to get all kind of access. Okay, time being, I will cover in particular, you kept for semester third only. In semester third, there are 4 theory courses as usual, and I think practical is annual, and 2 practical courses, including project assignment. Okay, this is very good. I think so. Just we will do for M.Sc. Not only just framing the syllabus, but also we are also doing job up to draw the question papers, and the evaluation is given to you for your college only. Okay, the point is very nice, so as to interact. So while framing, what kind of aims in our mind? Okay, we have made the syllabus in such that no doubt it will be very useful to set, get, net examination. Not only that, but also our aim is to again inculcate the nature of research in a particular students, in particular physical chemistry students. Okay, no doubt this paper name is solid state chemistry. No doubt it is a optional, but due to lack of teaching faculty, so therefore we are teaching this solid state chemistry, which is optional subject, no doubt, which is important component for MSc. Just for your brief, all the participant, brief introduction regarding why solid state chemistry. So recently we have received second highest citation to the university. The survey made by BRICS University. Okay, we are second in India. So even all IITs, all national institutes, so among them, our citation is number 2. Definitely credit goes to who is doing the solid state chemistry research. For your brief information, so physics group likely to be most 90% are doing the research in solid state chemistry. If you go through our library, so our library has thesis consist of more than 300 in solid state, and not only physics but also chemistry. So many faculties are engaging to do the research in solid state chemistry. Okay, therefore, so I will give just a brief idea about what kind of syllabus is included in our curricula in MSc course. So as usual, this consists of one thing. Also, we are 10th position in India in material science. Okay, these are the few remarkable achievements, and credit again goes to solid state chemistry. So there will be no boundary between organic, inorganic, analytical and physical. So even organic people are doing heterogeneous catalysis, and it is a need of the day. So previously 10 years back, organic people are doing only homogeneous reactions without using any catalyst, or using catalysts like acid catalysis, organic catalysis. Now it is a time, no doubt, heterogeneous catalysis are very popular with respect to separation. And one more thing, heterogeneous catalysis, it is very able to do modification. So one of the zeolite has a surface area is 600 meter square per gram. So here is the surface area, better is the reaction. So this is the key concept regarding heterogeneous. So therefore many solid like a platinum, like a palladium, so chemical, pharmaceutical as well as chemical reactions. So these are the very good materials for heterogeneous catalysis. So therefore, unless and until knowing the details of this, we can't go further. So in this case, course wise, so I will show you, no doubt. So solid state chemistry, even though it is optional, it is very important topic in case of chemistry. Okay, I will share my share screen. Is it possible to see my screen?
Yes, sir. Yes, sir.
Yes. Okay, as usual, myself is Garadkar. Shinde has introduced me. I am working as a professor of physical chemistry. Okay. Okay, what kind of research we are doing in university, not in chemistry department, in university. Chemistry department has involved broad canvas of research activity, competing basic as well as applied research. So in particular, solar cells, supercapacitor, thin films, nanoparticles, etc. As well, we are doing solution chemistry, catalysis. In particular, solid state and catalysis are related to each other. Again, synthetic chemistry. In particular, again, heterogeneous process by using synthetic chemistry, again related to material science. Heterocyclic chemistry heterocyclic compound formation by using again catalysis, heterogeneous. And last one is separation science known as a solvent extraction. So these are the few branches of good branches relating to research. Okay, why solid state chemistry? So I will go topic wise. So first topic is, I think, solid state. Okay, this is just introduction. Already we have introduced in solid state in B.Sc. 1, 2, 3. Not only B.Sc. 1, 2, 3, but also very good background is given in 10+2. So see, again it is very essential in M.Sc level, part 2, physical chemistry. So again we are very much related to nanomaterials. Again nanomaterials. So one should have a good background of material science. Till today there will be no any material without having material. You can tell me any single material without having material. So till answer is no. So everything is consist of a materials. Okay. So why solid state chemistry? The student will obtain required knowledge for understanding material science, material problems. Initially, they will study the structure of solids and get introduced with the importance of chemical and physical bonds, crystal disorder, and defects for materials properties. They will get insight into electronic structure of crystals and compare it with the electronic structure of nanomaterials. Okay, nanomaterial concept is not in solid state chemistry, but in particular materials, rather. Okay, see, as usual, solid consists of a three type of materials. One major consists of a crystalline material, another consists of a amorphous material. Okay, identification is very essential whether material is crystalline or amorphous. So what is the ultimately use of that material? If you see as an application, crystalline materials are very better than amorphous material. So what will be the proof? We are using solar panels. This is called as a solar cells. This is also called as a photovoltaic module. Okay. So roughly the area of 3 feet by 4 feet of a module, solar module, I'm talking about. Shivaji University, all the terraces occupying all the photovoltaic solar cells. So therefore, how much electricity generated by us will be tallied with electricity provided by MSEB. So therefore, we are using free of cost. Okay, by getting the grant from UGC and DST, all the university roofs are covered by solar module. Okay, typically this is again related to solar cell, is material science. In what way? As I said, there are two types, crystalline and amorphous. Okay, my statement is crystalline materials are very better than amorphous material, no doubt. There are two type of one material known as silicon is a material belongs to semiconductor. Silicon has again types polycrystalline material, amorphous material, and one more material naming is monocrystalline single crystal. Okay, I think many people this word is maybe heard about it, but see how it is same material silicon is in the form of polycrystalline, silicon in the form of amorphous material, silicon in the form of single crystal. Generally it is called as a monocrystal. No doubt top will be monocrystalline material. No doubt it is very costly. The purity of that material is 99.59, 99.999999. So 0.0000001% impurity. As percentage purity matters, cost is very high. So with respect to that, see what will be the efficiency. Okay, now, so there are no doubt, unless and until somebody is interested to purchase such kind of module, see if there will be SI with the polycrystalline, efficiency is limited. Silicon can be sold on the basis of polycrystalline and single crystalline. Okay, so general idea is no doubt crystalline material with single crystal and polycrystal. So how much difference cost wise? Double. So generally we will give more trace, which will be the low cost. No doubt it will be seems to be photovoltaic cell, but cost wise it will be lesser than a single crystal, and efficiency wise 10 or less than 10% difference. So how to distinguish this? As a general man, as a common man, how to distinguish? So this will be taught in solid state chemistry. Many aspects of modern life are dependent upon the availability of functional solids. Chemists are in strong position to contribute their synthesis. However, the chemist needs to be able to understand what are the trying to make it and why. Okay, the first topic introduction. What is a solid state chemistry? Laws of crystallography, also included in B.Sc. Lattice types, X-ray diffraction, Bragg's equation, Miller indices, Bragg's method, Debye error method of X-ray structure analysis of crystals. See, so this topic even seems to be very simple, and application of this. So you may go through any solid state material who is performing their PhD thesis. All the points are applicable to PhD student. Okay, in that one more, many also Nobel prizes are awarded to solid state chemistry, but in particular the investigation of X-ray. Okay, don't forget while teaching solid state chemistry the importance of X-ray. Without X-ray we can't do anything regarding solid state chemistry. So due to investigation of X-ray, unknown rays, Nobel Prize is given to Röntgen. The second prize, the who investigated the Bragg's equation, father and son, known as Bragg's, father and son. Again, they have awarded Nobel Prize. I definitely know what will be here, but awarded Nobel Prize with respect to identification of crystal structure. Okay, so how one may correlate? So material and the properties. See, just we are teaching simple cubic. With respect to how this is very important with respect to preparation and identification. So X-ray diffraction, no doubt, just it is a qualitative and quantitative. So first of all, as per the Bragg's equation, so Bragg's is nothing but a scattering of a X-ray with a construction. This is called as a constructive XRD patterns. No doubt, when X-rays are bombarded on a material, they will diffract. This is called as a scattering process. When it is out of phase, this will be known as a destructive. This is in phase, known as constructive. If it is constructive, you will get a peaks. Okay, the number of peaks obtained in XRD patterns, this will suggest that the material is of crystalline type. In particular, it is called as a polycrystalline type. It is very clear. This is given in B.Sc. NaCl, generally we used to give an example of NaCl. NaCl, polycrystalline material obtained 4 to 5 peaks. Based upon these 5 peaks and position, in general for organic chemist, any material having a peaks, so definitely you may say these are polycrystalline material. As I said, distinguish between polycrystalline, crystalline and single crystal. That can be obtained by X-ray diffraction. Again, in X-ray diffraction, single crystal diffraction, polycrystalline diffraction, even it is powder as well as films. So this kind of information can be obtained by X-ray diffraction. So therefore, while teaching to your students, tell the properties of X-ray. No doubt you may put again property before that. You may how X-rays are generated. Just metal target, electron beam bombarded to each other. Due to bombardment of these rays, X-ray will form. See, again, X-ray is a broad wavelength, right from 2 to 5 electron volt. Okay, sorry, nanometer. So depend upon target, that will get, no doubt X-ray will get polychromatic light, not a monochromatic. So I used to tell that why X-rays of copper target are used. This is very essential, and you must transfer the knowledge of such. Generally for X-ray, copper is used. Target of a copper is used. Answer is, the X-ray generated from copper, the wavelength of, no doubt, n number of wavelength are generated. In particular, we are using monochromatic copper target. So that has a rays 1.5406 angstrom in it. There will be filter while generating X-ray, only copper target. There are n number. Out of that, we are using 1.5406 angstrom target X-ray wavelength. Anybody will know why, participant? Why this kind of monochromatic X-rays are used for X-ray diffraction? Shinde? Participants are, I think, muted their volumes.
Yes, sir. Yes, sir.
Okay, anybody, Samadhan Pawar, are you able to say why X-rays are used for diffraction? Put your video off.
Hello.
Anybody can answer why X-rays of copper target are used for diffraction?
Because X-ray has highest frequency and higher energy.
Answer is no. However, we taught in M.Sc. when you are in M.Sc II class. I think X-ray I have taken in M.Sc II, semester 3rd.
Yes.
In that, I have given more trace. See, as I said, the wavelength is 1.5406. If you carefully see the interatomic distances of any material, so this close to 1.0. Interatomic distances of any material, solid material, as well as the wavelength of X-ray, which is of copper, 1.05406, 1.5 angstrom. So this distance are matching to each other. Answer is why X-ray? So this must be matches to interatomic distances. 1 or 2 gamma rays, 1 or 2 other rays. Answer is a proper diffraction.
Okay.
This is called as a constructive diffraction. Can be obtained only. This is called as a Bragg's condition. One Bragg's condition must diffract. Then second, constructive diffraction, and very good pattern can be obtained when such kind of X-ray, in particular copper target. No doubt there are n number of target, copper, molybdenum, chromium, etc. are there. In particular, copper target is better one. So therefore, such kind of information, okay, must be must be reached to students. Okay. So again, see, this is regarding X-ray. Second point. As usual, I have given information. Bragg's father and son has awarded Nobel Prize, no doubt. So this is very useful to identify structure. So there are only 7 structures are there. Okay. So these 7 structures, so related to stability, as well as, if you see, again a question may arise. So after studying the structure, what will be the use? Okay. So hexagonal structures are always better than cubic structures. Okay. Regarding stability with respect to temperature, with respect to stress, with respect to strain. Okay. See how this very important application. Say for example, my compound is cubic. Again, cubic has 3 types of Bravais lattices. Bravais is a German scientist. He has made maximum points in a lattice are arranged in such a way that the structure can be divided into 14 types. So this is called as a Bravais lattices. Okay, he is a German scientist. Again, he has also received a Nobel Prize. Okay, what is the use of that? So in a simple, in cube, there are 3 types again. One is simple, another is face, and another is body centered cubic. So out of that, so as a point of catalysis, so simple cubic, how many points in a unit cell? Okay, answer is only 1 point. Single unit, just a single point. So just what is mean by polycrystalline material? The repetitive unit of a single units in a material is known as a crystalline material. Okay, 3-dimensionally it is arranged. Just one simple cubic has a single point. Go to body centered, points are 3. Go to face centered cubic, the single unit consists of 4 units. Okay, as a point of active centers, as active centers are more, catalytic activity is more. Just we are teaching in catalysis. Active centers are more, catalytic activity is more. So out of 3, if you teach in such a way that number of points or active points are more, so that catalyst is better. So face centered cubic is always better up than simple, and no doubt simple is not so bad. But as a point of catalysis, so face centered cubic is better. Answer is it has 4 points. In this fashion, you may put such efforts to reach structures as well as applications. Okay. And last point we have covered is in that unit is device error method of X. No doubt in X-ray, so it is a bit heavy. So again, X-ray diffraction. So it is give idea about that how to identify the structures by getting the X-ray pattern. Okay, there are n number of methods: Bragg's method, sin square theta method, and as usual standard methods. You may teach a brief introduction of that. Details are not expected. Okay, as usual sin square theta. One systematic unit is there. This is called as a systematic absence of a HKL planes. Okay. See again, one more important point in this unit is Miller indices. We will take Weiss indices, take intercept. Okay, make it integration, then put the Miller indices. So generally Miller indices are considered better than Weiss indices. So again, okay, Miller indices are very characteristic properties of a particular material. Go into details. As I said, so there are 3 types of material, like a single crystal of silicon, polycrystalline material of a silicon, and amorphous material of silicon. Definitely, monocrystalline, single crystalline material of a silicon is better than these two with respect to photovoltaic cells. Okay, no doubt. Preparation varies costly. Price is again costly, but you may say give the sense in such that single crystal of silicon is very better. Okay, if single crystal, again Miller indices are different. Okay, till today 2020 we are able to prepare vapor. All the vapors are used in integrated circuits of mobiles, TVs, laptops. These are made up of single crystal silicon. Okay, so that's why so efficiency is very high. Okay, out of that, see how it is very important. The single crystal material with 110 orientation has again higher efficiency with respect to IC, with respect to it is a building block of a most of the component like laptop. So 110 which will be again higher. So in this fashion you may teach Miller indices importance. Last point in that unit is device error. Generally again we are distinguished between material, powder, this is comes under micrometer, nanomaterial comes under, as usual we are saying the definition 1 to 100 having the size, this is called as a nanomaterial, which will be different properties than the bulk. This will be roughly, not exactly, able to determine, known as device error equation. If you know the pattern on the basis of FWHM, we are able to say this equation is very important, and all the thesis of material science consist of this equation. I have covered this indexing. Okay, absence can so FCC, BCC, and simple cubic. On the basis of that, one may distinguish very better. This is called as a systematic absence. Okay, structure factor and relation intensity, that will be more related to again research. Try to give what will be the structure factor, intensity, and electron density. Higher is the electron density, higher is the basically conductivity. Likewise, this is enough in case of first unit. Second unit is again very important with respect to material formation. So as usual, it having 4 types: additive, structure sensitive, decomposition, phase transition reactions, tarnish reaction. Okay, this is bit given why solid state chemistry reactions are very difficult. So see, solid state chemistry is nothing but two solids kept together at a particular temperature. No doubt these reactions are very difficult. So solution chemistry is very simple. Okay, solution consists of cation and anion of reactant, both reactant. So they are very easily travel one place to another place due to media, like a solvent. Here there will be no any solvent. So reactions, no doubt, material having cations and anions. Cations are smaller, anions are bigger. So regarding cations are movable one place to another place, we are giving one example known as a tarnish reaction. Okay, no doubt. So solid state reactions are very difficult in solid state. So movement of a cation one place to another place forms the compound and interface. So it is very difficult, and even identification is very difficult. So Wagner has made experiment to keeping two solids together, and he found that so most of the cations are traveling one place to another place. So this is called as a sulfiding of a silver. Okay, he has taken silver bar, kept near to sulfur, molten sulfur. Okay, he found that the silver ions are traveling the place. There will be some 2 to 3 inches difference between these two, and found that Ag is transferred one place to another place. So this is benchmark to study the solid state reactions. In particular, these types of, okay, so many theses are related to additive. See, so now very important material like TiO2, zinc oxide, are very important material with respect to applications. If you combine two, zinc oxide and TiO2, again that will be gives one more material. So this is very good application as compared to individuals. So such kind of addition. So what requirement is essential for additive reactions? Okay, before additive, one must have a idea about the structures. Same structures are there, so that will form different material which is applicable. If the structures are very different, then it is very difficult to form a single material. So that's come under additive reactions. Okay, zinc oxide has its own properties. TiO2 has own properties. Combination of these two, merging of these two, gives one more properties which are better than this. Decomposition is nothing but just take the compound, heat it. It is in BSc 1+1. So just any compound, heat it. Along with gas, one solid compound is formed. Generally, this is related to heating. Oxides are formed. So by using this decomposition process, what are the gases and what are the products can be identified. Okay, last point is known as the structure affecting the reactivity of solid state reactions. So while doing such kind of reactions, so for solid state reaction, for example, I need to form a zinc oxide. Take any salt like zinc nitrate, heat it, you may get zinc oxide by addition of one of the impurity like europium. If you add europium in zinc oxide, the rate of reaction is very faster. So this will say regarding impurity may improve the formation activity. As well, what will be the state regarding zinc oxide formation? Zinc nitrate is in solid form. If we make it fine particle, reactivity is higher. This kind of concept is in factors affecting reactivity of solid state. So this is very easily available in many books. Okay, so this is third topic is very important and many people are doing research. So this is related to research again. Okay, metal, insulator and semiconductor. So in Shivaji University, we are doing very better in semiconductor. If you go in our library, so more than 500 theses are related to semiconductor. Okay, so just doping may has the degree of PhD. So that much importance for semiconductors. So two theories are related to metals, insulator and semiconductor. One is free electron theory and their applications. Electronic structure of solids. Say for example, question arises, in a periodic table, which will be highest conductivity of a metal? Metals are generally having both thermal conductivity and electronic conductivity. So this answer will be goes to on the basis of electronic structure of solids. Answer is electronic structure of silver is very better in the sense more number of electrons are available for silver. So therefore silver conductivity is very high. So therefore, but due to cost we are not using silver, but second most is copper. It is based upon this theory. Okay, band theory, no doubt in insulator free electron theory has limitations, only it is applicable to metals, not specified for semiconductors. So this will be available by band theory. Okay, band theory again very clearly distinguish between metal, insulator and semiconductor. So we are relating to semiconductor, so band theory will be useful. So this doping in semiconductors, So very useful. So just see, the concept of doping is nothing but very small amount. How much small? Concept of doping is one may add not more than 1% with a host so as to change the host properties. As I said, 500 theses are with us in Shivaji University based upon doping. So doping concept is very important. If you change the property by more amount, less than 1%, this will comes under composite. So as usual, one of the concept like a p-n junction, we are now using LEDs, light emitting diode, is nothing but junction of gallium arsenic is a junction between p-n junction, as usual. So this p-n junction formation has awarded Nobel Prize with respect to p-n junction. Such kind of information you may reach to students. Superconductor, I think today's Sakal paper has gives the idea about superconductor. So this just introduction. The material having highest conductivity at room temperature, low temperature. So this is known as, there will be no any resistance at that temperature, known as a superconductor. So superconductor has a very special properties. Just introduction. And last one is, okay, as usual, optical properties of organic semiconductors. So OLED, now the device having OLED, organic light emitting diodes, are better than LEDs and low cost. So they are flexible. So just introduction. Most of the time organic LEDs are using as a display. They are flexible. So due to conjugation, so as usual, power will know better. Luminescence properties, excitation, emission, we can make it tunable as per our requirement. So therefore, bit organic semiconductors like anthracene, tetracene, okay, are added into that. So luminescence and photoluminescence, both are same. So photoluminescence, as usual, just to give idea about students. So what is difference between fluorescence and phosphorescence? Absence of light, again known as bioluminescence. Such kind of luminescence properties and respective applications. Okay, I have given light emitting diodes, luminophoros, etc. So bit laser, principle of laser, etc. So we are using barcodes. It is based upon laser. So now cosmetic surgery based upon laser. So in particular, you may teach solid state laser. Okay, like ruby laser. This is known as Al2O3 doped with chromium. So this laser can has many applications. So what do you mean by laser? This is based upon concept of Einstein concept. Induced emission. Concept is induced emission. Emission is generally spontaneous. Here is induced. So based upon this concept, you may teach laser. No doubt, laser has in particular solid state laser, not gas laser. Okay. Unit 4, it is based upon single crystal material. Not so much involved in direct application. As I given one example of silicon, it is related to last topic. So single crystal materials of cadmium telluride, cadmium sulfide, etc. are very useful. So that's why first of all, put your efforts with respect to what do you mean by single crystal. Okay, single crystals. Then how to prepare seeds. What is the principle of nucleation that comes under this topic? Methods are there. Okay, so as a interest, so I think many people will know our Moite sir has created many single crystals, like ammonium diphosphate, like single crystals of copper sulfate, etc. So which will use very different properties than individuals. Okay, defects. We will teach to student at 10+2 Frankel defects, Schottky defects. So these defects are very favorable with respect to properties. Just doping may tune the properties of band gap. So 1 to 2 band gap is better material for solar cells. Okay, last point. I think many people is lacking the books. So for who is teaching solid state chemistry, one must have a models. If doesn't have, you can purchase the models. So unless and until taking the models, we can't teach. So cube, so cube, transparent cubes, you may show the cubes, lattice points, planes on the basis of models. So taking the models, that will be one may give the idea to NAC also. So this is comes under by using like models. Okay, this is very essential regarding solid state chemistry, and books is again important. So most of the books are available, like Principles of Solid State Chemistry, HV Keir. In particular, it is good for like single crystal growth. Solid State Chemistry by NB Hani, it is old book available with me as well as in library, Shivaji University. I think doesn't available to any colleges. This is very old book available, but there will be no any reprint. If anybody is interested, you may have this book with me. So this is the last one, solid state chemistry, just introduction. DK Chakravarti is of 300 rupees book, is available in any bookshop. Introduction of crystallography. This is again these two MJ available with library. Other is okay. So for for X-ray diffraction, best book. It is available in physics catalog in university, known as Elements of X-ray Diffraction by B.D. Kaliti. This is 2021 edition. This is reprinted in 2021. New book is of in dollar. I think more than $100, but it is available in library. If limited Xerox may be available to you. Solid state chemistry, if you interested more for research, you may read A.R. West. It is related to solid state chemistry, in particular free electron theory and band model theory. Electronics by Simple, this is like a superconductor, laser, etc. are given in Jacob books. Principles of Physical Metallurgy is in Abhijit Mulik. Okay, as usual, what are the NAC requires, what is the outcome of course? These are some outcome, no doubt. This is very useful course for PhD people. Everybody is shouting regarding material science. And so these are very good chemist, solid state chemist can be produced by outcome of this course. Okay. Any questions from participants? Make very video as well as mic on.
I request all the participants, if you have any question, please ask. Is there any question from the participant?
Hello, Gaikwad sir. Gaikwad sir, am I audible?
Yes, Shivaji Dada, yes, he is audible. Are you asking me or Gaikwad sir? Today you are asking questions to me. So your lecture is after my discussion. I think nobody has question. I think
okay, sir, I think there is no question from the audience.
Okay.
Hello, am I audible?
So Tade will start.
Yes. Sir, I am so much thankful to you, sir, for your kind lecture. Now I request Dr. Shivaji Taide, sir, to start their lecture.
Okay.
Sir, मी तुम्हाला होस्ट केलेलं आहे, सर. शिवाजी सर.
Okay, sir.
Please continue.
Hello. Sir, am I audible?
Yes, sir. Yes, you are audible, sir. Please continue, sir.
Okay, do you see my presentation now? Hello, sir.
Yes,
Do you
yes,
see
sir.
my
Yes, your
presentation?
presentation is on the screen, sir.
Okay, sir.
Please
So, how
continue,
much
sir.
time, sir, I am?
Sir,
Okay,
actually
sir.
40 minutes you have.
Okay, sir. I will wind up within 30 minutes or before that. No problem, sir. Within time, 3:30. Okay, sir. So, first of all, I am very much thankful of the organizing committee of this workshop who have given me an opportunity to talk something about the practicals of our third semester physical chemistry subject, which is recently we have changed the syllabus. And okay, so we will start with the practical. So that's why some protocol is essential for carrying out the practicals in laboratory. Okay, so here are some general protocols that we follow in our university campus that make pairing of the students. So pairing usually done according to the seat numbers, and then what we do, we assign them experiments. So for every batch, so for example, we have 20 students. So we have 10 pairs and we have total 13 experiments. So initially what we do, we assign one experiment to one pair and we instruct them to find a practical procedure. Okay, actually we never do spin feeding to students. Actually, we usually say them just go into library and find the procedure. Since in colleges there is some limitation due to lack of availability of books. Okay, but by the way, we can sort out this problem. If you want some Xerox copies of the practical procedures, we can provide you. Okay, you just ask us for that. We will provide you, no problem. Then after the students come with their procedure, we check their procedure. Okay, and we usually ask students to maintain the record because for one practical they find at least 3-4 procedures, and from that 3-4 procedures we select any one, and after that next we ask them to find out the different methods of standardization like titrimetric methods. Usually whenever we perform some experiments, before carrying out the experiment we have to standardize all the analyte that we are using for that experiment. So usually we ask them what are the different procedure, how we can standardize, for example, NaOH, HCl or KiO3, sodium acetate, silver nitrate, okay, ferric aluminum. These are the different chemicals that we are using, and we usually ask them first, you must find out the procedure first, finding out the standardization procedure for this, how we can standardize. Then we instruct them for finding the procedure of equipment standardization. They must know the importance of standardization of analyte as well as they must know the importance of standardization of instrument. Because as far as physical chemistry is concerned, we are only approach to the accuracy or just near the accuracy if we have a standard chemicals and standardized procedures and standardized equipment. So usually we ask them to collect the procedure for pH meter, potentiometer and other standardization. Also we allow students to work themselves rather. Okay, that's it. Now, these are some list of the experiments in our semester number 3, that is determination of stability constant of ferric trisalicylate complex. Then to determine the stoichiometry and stability constant of ferric salicylate complex. Jobs method by Jobs method and Mohr-Ratio method spectrophotometrically. Then stoichiometry and stability constant of silver aluminum complex. This we do by potentiometry. Then transport number for using moving boundary methods, we determine the transport number. Then determination of critical mycelic concentration. This is related to conductometric analysis. Then determination of equivalent conductance at infinite dilution and dissociation constant of weak acid by Fowler's law. 6. pH metric determination of carbonic acid. Then crash we study also some like using the depression and freezing point method. We measure the molecular weight of some organic acids in benzene solvents, and then we also by titration method. This is non-instrumental techniques of estimating the rate of reactions, where we perform the titration for measuring the order of reaction between iron acid and acid. Determination of the apparent molar and partial molar volume. Here we determine the partial molar volume of the using this trigonometric method, where we measure the density at constant temperature, and using the different equations we find out the partial molar volume. Then 11, 12, 13, these three experiments are related to the quantum calculations. Okay, structure drawing, geometry optimization, single point energy calculation. I think in the first session, morning session, Professor Dagade sir have explained the different theoretical methods and the different software. I think he must have mentioned in his lecture that which are the different softwares by which we could able to calculate the different things. I will enlist you different softwares at the end of this presentation, and there we will see that how we can estimate these things. Okay, so let us begin with the stoichiometric determination and stability constant of ferricyanide complex by job method and mode ratio method spectrophotometrically. Okay, so this is the experiment deals with the spectrophotometry, and we know that spectrophotometry is involving absorption of radiation by the matter. Okay, so in this method, normally we estimate the complex formation by using spectrophotometer. Our complex is usually formed between metal and ligand, and we know that the complex is maybe 1:1 or 1:2. So usually when we have to go for Jobs method and this stoichiometric mode ratio method, okay, in that case usually we prefer the complexes which are usually in 1:1 form. Okay, so in this first experiment we will be dealing with the formation of ferric salicylate complex. So we are using different analytes. So normally we have NaOH, HCl, sodium thiosulfate, okay, and potassium hydrogen thiosulfate, ferric anion and all. So what we will do, we will first prepare the solution, okay, and in the beginning of any experiment, before going to the actual analysis of the analyte, we usually start with the standardization. So first we use potassium hydrogen thalate to standardize NaOH. Then that NaOH which we standardize with KSP will be used for standardization of HCl, and then further standardization we carry out, for example, sodium thiosulfate, which we use from, okay, in the titration. Okay. So we standardize it with then after standardizing this KOC, okay, we standardize the ferric solution, okay, and we solution. So for the standardization of sodium thiosulfate solution, what we are solution, what we are doing there is the copper added catalyst. So copper added catalyst is prepared by using copper sulfate and KI. In 1:1 proportion, we can use it, and we can standardize this ferric aluminum using each of KI and starch as an indicator. Okay. After the standardization procedure is over in this experiment, okay, what we do, we go for determining the wavelength of maximum, that is lambda max, using, okay, Gauss method, where we take the fixed concentration of ligand and fixed concentration of the metal, and just we are varying the volume of ligands and metal continuously, and we get the inverted bell shape perfect UV spectrum, visible spectra or visible spectra, depending on the wavelength of absorption. We get the proper spectrum, bell shape spectrum, and from the absorption maximum we determine the wavelength of maximum.
शिवाजी सर, हॅलो
हॅलो,
हा सर, आवाज थोडा कमी येतोय तुमचा जरा.
आवाज कमी येतोय सर?
हा, आवाज तुमचा कमी येतोय जरा.
1 सेकंड सर. हॅलो, आता येतोय सर?
हा, येस येस सर, येस.
Okay. Okay. So in this experiment, we have to determine the stoichiometry and stability constant of the ferric salicylate complex. So how do we start with this experiment? Usually we used to ask the student that what are the chemicals needed for carrying out this experiment. So they make a list of the chemicals, they prepare themselves, and then we ask them to standardize these chemicals. Okay. So usually they do the standardization. For example, here I have shown potassium hydrogen thalate solution is a primary standard solution. So using this primary standard solution, they standardize NaOH, and then from NaOH HCl. Okay, and then sodium thiosulfate by using KiO3, and using that sodium thiosulfate, okay, we standardize the ferric aluminum solution using copper added as catalyst. Okay, so this catalyst we prepare by using copper sulfate and iodide. So we use at least one or two pinch of this catalyst, ferric aluminum. and solid Ki and 1 to 2 drops of that. Okay, and using starch indicator we standardize this. Okay, after the standardization is over, then we proceed. So what is the purpose of the standardization? Since we are doing the spectrophotometric analysis, which are essentially carried or based, which are essentially based on the Beers-Lambert's law, and we know that the Beers-Lambert's law is strictly valid only for certain concentration. Means it is valid. Usually say that it is valid only for the absorption below 1. Okay, above 1 the validity is somehow the results of absorption are mislead. So therefore, we first standardize the analyte like ferric and salicylic acid, and then we prepare the complex in such a way that the absorption should not go beyond 1, or it should at least reach below 1. So using that, we first go for the finding of the absorption maxima. So using Jaws method, we do it, and from that plot, we measure the stoichiometry of solution, and then from stoichiometry of the solution, okay, we go for the mole ratio method, where we vary the concentration of the ligand by fixing the metal, or we fix the metal and vary the concentration of ligand, and generates a plot, and from that plot, we have absorption maxima and absorption, like say for example, I have to go for this formation of a complex. So let's say that what I will do first, I will prepare for mole ratio method. Okay, for mole ratio method, what I will do, I will fix the concentration of ferric and vary the concentration of ligand. Or you can also do fix the concentration of metal and vary the concentration of ligand. Okay, so if you vary the concentration of the metal by fixing the concentration of ligand, okay, we get the in mole ratio plot, we get the absorption increment up to certain concentration of AAC, and then later on, even if you increase the concentration because of all there is no further rise in the concentration. Okay, so what we do with this curve, we plot absorption maximum. Okay, we plot the standard curve of absorption versus concentration, because your y-axis is absorption and your x-axis is concentration of Fe3+, which we are using for this. And from this plot, what we generate the two things. One is absorption maxima, and second one is the absorption. So by extrapolating this line, okay, and then taking the perpendicular from here, okay, we find out the two concentration here, and so we find out the A max and A. So by taking the ratio of A by A max, so upper value of absorption is A max, lower value of absorption is A. So by taking A by A max, we find out the value of alpha. And alpha is nothing but the, it's a fractional number varying between 0 to 1, which we used to calculate the value, which is used for the calculation of the stability constant of this complex. Okay, so if you write the equation on this, one side we have to write the ferric, one side we have to write the ligand, and another side we have to write the complex. So if I take this ferric as alpha, complex as alpha, then this would be equal to 1 minus alpha. So K is equal to 1 minus alpha upon alpha square. So using this value of alpha, okay, we can easily find out the value of stability constant. Our second experiment is determination of the stability constant of ferric trisulfide complex. This one is also similar to the previous experiment. In this experiment also, we go through the same calculation. Okay. Now, important thing is that the books, because we can do the experiment, we can do the calculation, but for that we must know the source. Okay. So this experiment is available in Hogel's textbook on page number 13, 33, and 44. If you go to the page number 13, 33, and 1347 of 6th edition, okay, Hogel's textbook of quantitative analysis, 6th edition, you would find all this experiment with the procedure. What just you have to do is that how to perform this experiment is very important. Okay, so we have to be take care of whenever we see the spectrophotometer as a quantitative analytical tool. Okay, we have to take care of the Beers-Lambert's law for this experiment. Our concentration must be below 1 all the time. Okay. Second one is determination of stoichiometric constant and instability constant of silver ammonia complex. Okay. So this is actually potentiometric experiment. In this potentiometric experiment, what we do, we prepare the silver electrode. Okay, we have one silver electrode and one compartment. Okay, so we take the two silver rod. Am I audible?
Audible.
Okay, so we take the two electrodes, okay, two silver rods, okay, in one compartment we have a complex. That means from burette we add the ammonia, from burette we add the ammonia solution. in fixed concentration of a silver. Okay, and in another compartment we have only Ag. Okay, and with this, what we do, we measure the activity of Ag, and in another compartment we have after each addition of silver, after each addition of ammonia from the burette, okay, we have different values of the potential, and we plot the graph of potential versus the concentration of silver, and based on that we have a two equivalence point, one for 1:1 complex, another for 1:2 complex. Okay, so based on the concentration limits of 1:1 complex and 1:2 complex, what we do, we prepare the 1:1 and 1:2 silver ammonia complexes, and we measure their potential, we measure their activity of silver, and using the calculations, using the formulas given in the experiments, okay, we go for the analysis of this. Okay, so what we determine in this complex, in this case, that silver ammonia complex is, see, when we take the silver ammonia complex, the silver ammonia complex is obtained in two stoichiometry. One is in the 1:1, other one is in the 1:2. Okay, so we find out the limits where up to what limit of the concentration of the ammonia and silver there is 1:1 complex, and what limit of silver to ammonia there is 1:2 complex. So estimating that concentration from the plot of the potential versus concentration of silver. Okay, what we do, we measure the concentration of silver from the potential analysis, and using that, okay, we find out the instability constant for this. Okay, your okay. Our third experiment is determination of the transport number of H plus ion, Na plus ion, and K plus ion using moving boundary method. Okay, so previous two experiments were based on the spectrophotometer, and three experiments, two were on the spectrophotometer, the last one was on the potentiometer, and this is typically different experiment, and this experiment is depending on the DC power sources. Okay, so in this experiment, what we do, we take the two electrode, okay, and we apply the potential between the two electrodes. So usually in this experiment, we use a burette like this. Okay, so this burette is open in burette, and it is calibrated burette. So scale is given on this, and on this side there is one electrode, and on upper side there is another electrode. Okay, so there are the two electrodes that we are using, and we are applying a DC potential to these two electrodes. One is we kept at negative electrode, and another we kept at the positive electrode. And the electrolyte solution means the analyte whose transport number has to be determined. We fill this burette with that analyte. For example, if we have to determine the transport number of H plus ion, we use HCl as electrolyte. If we want to determine for sodium, we use NaCl, and for potassium, we use KCl solution. Okay, so we fill this burette with that electrolyte, and we apply the potential. Since these are all electrolytes, when we apply the potential, what will happen? The oppositely charged ions will move towards the opposite charge electrode. Since here H plus is existing the positive charge, so H plus will move towards the negative electrode, and Cl minus is in negative form, so it will move towards the positive electrode. As a result of this, what will happen? The concentration of the proton will be varying as there is a movement of the H plus ion. Okay, so to visualize this boundary, what we do? We add indicator in HCl solution. So we know that HCl is acid, and if we add some indicator, it will show color change. So normally methylene we use bromocrystal blue as an indicator for this experiment. So complete solution will appear as a blue, and if we apply potential after some time interval of, let's say, 5 minutes, you can see a small visible boundary at this point. And as the time goes on, the H plus ion will move in the upward direction, and because of the pH change, what we can observe that the boundary is moving in the upward direction. Okay, so in this particular experiment, what we measure the movement of the boundary. Okay, so already this burette is calibrated, so we measure the time required for the movement of 1 ml. Okay, from 1 to 2, how much time is taken by boundary. We measure that time, and using that time and that 1 ml volume, okay, we measure the transport number like using this formula. Transport number is nothing but it is volume multiplied by concentration of the analyte that we are using the burette. F is the Faraday constant. J plus is the charge on the cation which we are using as an analyte. I is the current that we are applying to the electrode. Means there are two ways of applying the potential to these two electrodes. Okay, one we can do the galvanostatic analysis as well as we can do the potential static analysis. Okay, since we apply the constant current, we call it as a galvanostatic analysis. And okay, by substituting all this value, V is nothing but it is the volume. Volume means we are crossing 1 ml of volume. So 1 ml is converted into liter. So 1 into 10 raised to minus 3 it will be in the liter. And C is the concentration of HCl. We can take the different concentration 0.01, 0.51 molar like that. As well as F is 96500. This is Faraday constant in coulombs per mole. I is the current, okay, which we are using 1 ampere, 2 ampere, 3 ampere, and Z plus is the charge on the cation. So in this experiment, what we can do, we can perform the transport number analysis by varying the current, as well as we can do the analysis by varying the concentration of the analyte. Okay. Now, what is the beauty of this experiment is that in this experiment we have to use the electrode which must be reversible with the ions that are actually under study. So we use here silver chloride electrode, and to construct the silver chloride electrode, we take the platinum wire, and on this platinum wire first we deposit the silver ion by using negative charge. Okay, by applying the negative potential, take the two platinum rod. Okay, the platinum rod which is at positive charge. Okay, which is at negative charge, the silver ion will deposit on this negative electrode, and after some time, okay, remove this electrode. Once you see the deposition of the silver on platinum, just wash it and again dip it in the chloride HCl solution and apply the positive potential. So there will be deposition of Cl minus ion on that electrode. So we get the electrode platinum AgCl, and which we call as a platinum AgCl, and we call that electrode as a AgCl electrode, which we use in this capillary experiment and from the top side. And our bottom side electrode is usually the cadmium electrode that we use in this experiment. Okay, so using this formula, we measure transport number. Now, student must know what is transport number. Transport number is nothing but is the fraction of the current carried by the individual ions, maybe cations or anions. Once you measure the transport number of cation, definitely the anion which is associated with that can be determined using the formula T plus is equal to 1 minus T minus, or T minus is equal to 1 minus T plus, because T plus T minus is equal to 1. That's why we can convert the transport number to each other using the formula. Okay, our third experiment is determination of the equivalent conductance at infinite dilution and dissociation constant for weak acid using Euler's law of independent ionic now we know that the weak electrolytes are very difficult to dissociate, and therefore it is hardly possible to get the exact dissociation constant of the weak acid. So for development of the determination of the weak acid, Euler's have given an important concept, and according to his concept, what he says that if we measure the equivalent conductance of the electrolyte solution at infinite dilution, the equivalent conductance of that electrolyte is equal to the sum of the conductance of the individual ions involved in that electrolyte. For example, here what we can say that we have a electrolyte CH3COOH, which is very weak electrolyte, and this CH3COOH electrolyte can be split up like this. So we can split up this CH3COOH electrolyte like this. In this case, we have Na and Cl extra. So therefore, to get the CH3COOH, we just subtract the conductance of the NaCl from that. So what we do to determine the equivalent conductance of acetic acid, we measure the equivalent conductance of sodium acetate, we measure the equivalent conductance of HCl at different concentration, we measure the equivalent conductance of NaCl at different concentration, and what we do, we take the intercept. Okay, so we find out the equivalent conductance of these electrolyte at infinite dilution situation. What do you mean by infinite dilute situation? Infinite dilution means where the concentration is very negligible. When the concentration of electrolyte solution is negligible, it does indicate that there is a quite large spacing between the cations and anion, and hence we can say that each ion is behaving independently. or sometimes it is considered to be as an ideal condition, and sometimes we exactly cannot say that the ions in vacuum, but it is synonymous to the ions in vacuum when we take very dilute electrolyte. So all the results which we take in dilute electrolyte solutions, okay, those are ideal because of minimum ion-ion interactions and ion-solvent interaction exist in that. Okay, so in this particular experiment, what we have to do, we have to prepare the HCl solution, initial solution, sodium acetate solution. We have to prepare their different concentration. We have to measure their conductance. Okay, and from conductance we have to go for specific conductance. From specific conductance we have to go for equivalent conductance. Okay, and then get the plot of equivalent conductance versus square root of concentration. Okay, and from that plot, okay, find out the intercept on the y-axis. Whatever intercept you get, that will be the equivalent conductance of acetic acid. For acetic acid, sodium acetate. For HCl it is okay, and for NaCl. And then arrange the equivalent conductance value in this way. You will definitely find out the equivalent conductance of this. Okay, there is alternative way by which we also find out the things. Okay, now we know that this is indirect equivalent conductance. We can also find out we can take the different concentration of the acetic acid, okay, and measure the equivalent conductance of acetic acid, okay, and then for each equivalent conductance, okay, find out lambda measured indirectly divided by lambda measured directly divided by lambda measured indirectly. This will be the value of alpha, okay, and from the value of alpha you can find out the instability constant for this. Okay, so using the Kohler's law we can estimate the dissociation constant, as well as, okay, we can find out the equivalent conductance of that infinitely dilute electrolyte. For this experiment, you can refer the book Introduction to Electrochemistry by Samuel Glasston. The page numbers are 172, 174, 201, 230, 261 to 263. Okay, on these page numbers, you can see our entire theory related to the conductance, related to the Kohler's law, okay, and all the ion-ion interaction equations involved, like the Biochemical equation. Then, okay, all these theories you can see on this page. So entirely you can understand what is this importance of dissociation constant, and how one can estimate the dissociation constant of the weak electrolyte. Next experiment is determination of the critical micelle concentration of a given surfactant in aqueous and salt solution. Okay, so we know that micelles is nothing but it is the agglomerated form of the or we can say that the polymeric form of the surfactant. Okay, so what happens when we keep on increasing the concentration of the surfactant in a beaker? Okay, what will happen? The surfactant will arrange themselves in the form of micelles. Okay, in the form of micellar structures. So anywhere from internet you can see the structures depending on the what type of the solvent you are using for solubilizing the surfactant, whether you are using aqueous or organic solvent. Depending on that, there is orientation of the molecules in the micelles. So what is the difference between the surfactant and the micelle? There is a huge difference in their properties, like conductivity. So when we take the surfactant without micelle form, its conductivity is very low, but when we take the micelles, its conductivity is very high. So whatever when we take the micelles, okay, immediately what will happen? If we take the conductance measurement at different concentration, and as we keep on increasing the concentration of the surfactant, what will happen? The micellization formation occurs, and at one particular point you will see that there is sharp rise in the conductance. So that point is our equivalence point, and that is the concentration over which the conductance is sharply rises. That point is representing the critical micellar concentration. So what we have to do in this experiment, we have to take care while preparation of the surfactant solution that there should not be a single bubble formation while preparing the surfactant solution. Okay, so prepare the different concentrations of the surfactant solution and measure their conductance, and from the graph only you will easily find out the value of the micelles. But you must know the various properties of the surfactant, because dominantly surfactant industries is keep on growing, and the properties of this surfactant, like micellizations, are normally called as a nanoreactors for most of the organic transformation. They are also used as a template for nanostructure formations, and there is huge importance of this micellization. So therefore you must know all the theory of this. So for this you can refer the book by Experimental Physical Chemistry by Halpern and Magdalen. You can also read the DJ Shaw book of surface chemistry for reading more in detail about this. Also, our experiment is pH metric determination of the dissociation constant of carbonic acid. What is the importance of taking this experiment is that we must understand the pH changes in our body, because all the reactions, enzymatic reactions in our body are controlled by the pH variation, or all intracellular reactions are controlled by the pH variation. So you must know that the mechanism of exhalation of CO2 from our body, that in the from bicarbonate form to carbon dioxide dissolved to carbon dioxide in the gaseous form, how the process is occurring. Okay, to understand that whole process, this experiment is designed. You can see the whole detail of this experiment in the instrumental methods of analysis on page number 674, 677, 680. Also, you can see the detail of this experiment in Lininger's Principles of Biochemistry book on page number 56, 59, 60, and 62 and 63. Okay. Now we will not go in details, all details of how blood pH varies and how the potassium sodium found in detail. Okay, you can read from these page numbers, easily you can understand the things. Okay, so this is pH metric titration, where we take the calcium carbonate in the beaker and we titrate with HCl. So when there is a replacement of the replacement of the sodium by H, there will be formation of the H2CO3. Okay, and then we get the two dissociation constants for first proton replacement and the second proton replacement. Another experiment is determination of the order of reaction for iodination of acetone catalyzed by acid with reference to acetone iodine and acid catalyst. Okay, so in this experiment, actually what we have to see, the reaction between iodine and acetone. Okay, and the catalyst we are using as an acid. Okay, so to study this reaction, okay, what is essential is to find out the rate constant and the in this experiment, what we will do, we will prepare the four set of solution. We take acetone, HCl, and iodine. Okay. So what is the if you look at this table, when you compare any two values, okay, what you will see that there is a variation of one thing. Okay. If you compare the first two rows of the table, what do you see that here water is constant? Definitely, it will not play any role. HCl is constant. Here it is 1 molar. Here it is 1 molar. And iodine is also constant, 0.05 molar, 0.05 molar. So within the first set, what we will see the variation of the acetone. If you compare the set number 2 and 3, okay, in this 2 and 3, what is the variation? In 2 and 3, there is a variation between, you can take the variation between this 2 and, okay. So there is a variation between there is a variation between here two more acetone is constant. So we have studied here variation between the acid. Okay. So to go for this, what we can do, we compare the set number 1 and 4. Okay. If we compare 1 and 2, there is variation of acetone. If we compare 1 and 4, okay, there is variation of iodine. And if we compare 1 and 2, okay, there is to 1 and 2, there is a variation of the acid. So this way we take the three things variable: acetone, HCl, and iodine, and what we do, we prepare this mixture. Now to prepare this mixture, you can take the total volume of the system as a 10 ml. That means you can take the first set is equal to 10 ml, second set 10 ml, third set 10 ml, and fourth set 10 ml. And according to you can reduce the experimental volume for this, and titrate this with respect to sodium thiosulfate and measure the reading at the interval of 2 minutes. Okay, and from that you would find out the rate of reaction and the rate constant. Okay, so for this experiment you can refer the August book of quantitative analysis. You can go through page number 374 and 378. All the details of calculations are given, as well as you can go to the practical physical chemistry by James and Richard book, third edition, page number 210, 189, and 193. Okay, so I am giving you detail regarding the sources of these experiments. So instead of explaining in all details, okay, you can just go through these books on this page number directly. You get these procedures. Okay, if books are not available, we can ask one of your you can come to us. We have these books. We can give you printout, no problem. Next experiment is cryoscopic determination of a molecular weight of organic acid in non-aqueous volatile solvent. So now organic acid is here, we use benzoic acid, and the organic solvent we are using here benzene. Okay, so this is again colligative property measurement, where we study the depression in freezing point while adding benzoic acid in benzene. Okay, we study the delta TF, that is the difference in the freezing point between the pure solvent and their solution, and using that depression in freezing point delta TF value, okay, we measure this molecular weight of the solid. That is, we measure the molecular weight of the acid which we are adding. Means we can measure the molecular weight of benzoic acid. So in this experiment, what we have to do, we have to use the Beckman's thermometer. The beauty of the Beckman's thermometer is that about its accuracy. It is 0.01 degrees Celsius accurate, and it is normally used for qualitative property measurement. So here, what we do, here we measure the molecular weight of the solute which we are adding into the organic solvent. What we have to do here, we have to first measure the freezing point of pure benzene, and then we have to prepare the different concentration of benzoic acid in benzene, and we have to measure the freezing point of that different concentration of the solutions of benzoic acid in benzene, and take the difference delta T between the solvent and the solution. Okay, so we have different reading for different concentration. Just substitute all this value K of 1000 W2 W1 into delta TF. So if you substitute in this equation, okay, what you will measure, you will measure the molecular weight of the benzoic acid. So initially you will get the exact molecular weight of benzoic acid in the lower concentration, but as you keep on increasing the concentration, you will find that the value of M2 is increasing and it becomes twice and thrice to benzoic acid value. So this indicates that there is a formation of dimerization and trimerization. Okay. So this is one experiment. In this experiment, what we have to do, we have to take the precaution that benzene is very carcinogenous. So while handling benzene, it should not be come in contact with our skin. Okay, there is a special apparatus. So you can take the beaker and in a big pot, you take the ice. In that ice, you take the your system and just measure the freezing point of the benzene and the solution, take the difference, and using these calculations you will come to know this equation. Okay, so detail of the theory and other calculations are given in these two books, Experiments in Physical Chemistry by Shoemaker, on page number 132 to 140. Whole detail of this experiment means standardization of Beckman's thermometer, how do we standardize it, okay, and how to take the readings, and all details are given on this. Second book you can refer, that is Spindler's Practical Physical Chemistry. It is revised and edited by Levitt. You can go to the page number 109 to 170. Whole detail is given. Then next experiment is determination of the apparent and partial molar volume of an S21 electrolyte using picnometer. Okay. So now these two quantities, apparent molar volume and partial molar volume, that can be determined using the density. Okay. So normally these are the two diagrams of picnometer. One is like this, where thermometer has scale. Other diagram is like this. So what you have to do, you just have to take the system whose analysis has to be done. You have to fill the system. So for example, I have to determine the apparent and partial molar volume of any scale electrolyte, because it is 1:1. So what you have to do, we have to prepare the solution of NaCl with a different concentration. First concentration fill in this picnometer. Okay, and you should fill it after filling this picnometer. You add this or it. So whatever excess volume is there, it will be automatically removed, and keep it at constant temperature. And after keeping the constant temperature, once the system inside it attains this constant temperature, just measure the density, measure the weight of this, and then relative density of the solution. Keep on measuring the relative density of the solution, and then based on the density calculation, we get the apparent molar volume. Then we can measure the specific volume, and from specific volume, molar volume. Okay, and details of all this calculation, from density how we can go for specific volume, then from specific volume how we can go for molar volume, and then apparent molar volume. Okay, all the detail of the calculations are given in this book, Experiments in Physical Chemistry by Shoemaker and Spindler's Practical Physical Chemistry. Okay, these two books are very important, and their entire entire equilibrium experiments are, or wherever you have to measure the thermodynamic properties. Okay, these two books are very essential. Okay, so the entire description of this experiment is given in these two books. You go through this book, Experiments in Physical Chemistry by Shoemaker and by Spindler. Then our 11, 12 and 13, these are the entire quantum calculation based experiments. You don't have to do experiments in the laboratory. We have one software. Okay. Okay, so we can measure the structure drawing. We can do the drawing of in small molecules. We can find out the geometry optimization, and we can do the single point energy calculation of that small molecules. Okay. Similarly, chapter experiment number 12. Okay, optimization of the single point energy calculation of small molecule and correlation on basis point, semi-empirical quantum calculation, and determination of the thermochemical properties of small molecule. All these quantum chemical calculations can be done using this following software. We can use the Gamma software. I think Douglas sir have mentioned all the software: Gamma software, MOPAC, Orca, QChem, Quantum, Espresso. Okay, all these need registration. Okay, when you download this, Gamma software is freely available, but when you download this MOPAC, QChem, okay, they need registration. Okay. Again for this 12 and 13 experiment, you can go through this visualization and input generation. For visualization and input generation, we can refer these two software, Avogadro and Gabrit. Professor Douglas sir have shown me this Gabrit software in the morning, and this is very user friendly. Even without knowing anything, okay, you can simply by rolling one standard experiment, you can go for calculation of the small molecules like water, carbon dioxide, okay, and interaction between the small molecules. You can easily study using this gadget software. Okay, this software is like this, where the periodic table is given, and using this periodic table, we can choose the any elements, small molecule, whichever we have to prepare. The structure is generated, and on the right hand corner, you can see that different properties we can study. And using this software, we can measure all these properties, like we can do the single point energy calculation, we can also do the geometry optimization, and also we do the quantum chemical or thermochemical property analysis of the small molecules. Okay? And that's it. That's all for the semester 3 practical. I think it is hardly possible to manage everything within a short interval of time. But separately, if you have some problem or any query, you can mail me directly. I will help you in the possible ways. Thank you.
Thank you, sir. Thank you very much. Any question from the participant?
Yes, sir. I have one question, sir.
Yes, ma'am. Please.
Yes. Sir, all practicals initially up to 10. We have well aware of that. But the practicals which are based on the quantum chemical calculations means they need softwares. Okay.
Yes, they need software, and they are freely available. I have mentioned you the list of software. You can see the list of software. I just downloaded this Gabit because in the morning only I downloaded this Gabit software. For this software, okay, this is freely available. Even you can go for Gamma software, it is freely available. If you download the Gamma software, okay, there is one help option is given. If you go into the help option, the algorithms and whatever is essential for carrying out some experiment. For example, if you create a cluster of 3 water molecules, and if you study the interaction and the structure and thermodynamics of the 3 water molecules, okay, the program is given. You can go through that program. Otherwise, if your students are interested, they can come to university, 1 or 2 students, and we will give them demo. They will learn, and they can teach to other students of your colleges. No problem.
Yes, sir. That is my question, because directly, if you are able to give demo for us, I think for Shahu College also.
Ma'am, any voluntary 2 or 3 students you send to us, okay, we will train them properly, and then they can teach in your colleges. No problem.
Okay, sir. Okay, thank you very much.
Okay, thank you, sir. Is there any other question from the participant?
One more thing is there, sir. One more thing is that since if you read the syllabus copy properly, sir, I have mentioned that the project has to be initiated from semester number 3. So at least in semester number 3, we must give them idea that what they can do, and then the actual experiment they will do in 4th semester. So our time will, the theoretical time, that is referencing time, will be saved if you follow this.
Okay, sir. Thank you, sir. Is there any other question from the participant? Okay, I think there is no question. Now, thank you, sir. Thank you very much. Now I request the head of Department of Chemistry, Dr. S.V. Patil, sir, to propose the vote of thanks.
Myself, Dr. S.V. Patil, Head Department of Chemistry. A very good afternoon to all. It gives me an immense pleasure to deliver the vote of thanks on the occasion of syllabus change workshop of M.Sc. Part 2, Semester 3rd, Physical Chemistry course organized by the Department of Chemistry, Rajarshi Chhatrapati Shahu College, Kolhapur. My special gratitude to our keynote speaker, Professor Dr. G.S. Gokavi sir, a eminent personality and Head Department of Chemistry, Shivaji University, Kolhapur. I would like to say thanks to resource persons of workshop. All are from Shivaji University Chemistry Department. Those who have prepared a syllabus for M.Sc course. That are Professor Dr. G.S. Gokavi sir, Dr. G.B. Kolekar sir, Dr. K.M. Garadkar sir, Dr. S.N. Taide sir, Dr. D.H. Dagde sir. My special thanks to our principal, Dr. S.T. Salunke, who has motivated us for this workshop. I would like to say thanks to our patrons and Shivaji University for giving opportunity to organize the workshop. Thanks to participants, colleagues, students who joined and participated in this workshop. Once again, I thank one and all. Thank you.